Hi, Marika, should I try sharing my screen to see if it works?
Yes, if you would.
Great.
Do you need me to stop sharing now, Jeff?
Yeah, that should be okay. I mean, I can just share my screen and it'll override yours, but it doesn't matter. So I'm just going to make a couple of announcements now. We've got about 123 participants, so might as well do it now. And then you can share your screen again. Okay. Okay. Good evening, good afternoon, good morning to everybody. Welcome to day 4 of Strings 2020. As usual, I want to just inform you of some of our rules of engagement and just tell you about what's going to be happening during the day. So again, I want to remind you to read and abide by our code of conduct, which can be found on the webpage. I'd like to ask that questions be kept to the end of the talk as usual, just to keep the flow of the talk going. To ask a question, could you please use the raise hand feature and wait to be called by the session chair? And we'd like to ask that you please remain on mute otherwise. You can use the chat feature of Zoom to ask a physics question to everyone or ask any organizational questions privately to an organizer. That would be anyone that's listed as a host or a co-host. And then I would like to remind you that we've set up Slack channels to continue discussions at any time, really. The Slack channels are open at all times. And then at the end of the day today, following on from the first 2 days of the conference, we're going to set up some breakaway rooms for the talks, and we'll group them in themes. And I will send out a notice toward the end of the day to remind everybody to just tell me which rooms they would like to go to. You can be placed in a room, and then you can ask to move a room should you want to. But unfortunately, the way Zoom is set up, the host, that being me, is the only person that can move people between rooms. I want to say as well that in addition to the usual breakaway rooms that we've had over the last couple of days, today's a little bit special because we're going to be hosting the Gen Het collective, who are going to be having a roundtable discussion in a breakaway room on inclusivity and diversity in string theory. More on this will be posted a little later in the day, and you're all encouraged to participate in the discussion. It will be another breakaway room, so again, you can ask to be moved into there toward the end of the day. So our first session is going to be chaired by Marika Taylor from Southampton, who will introduce the first speaker of the day.
Thank you very much, Jeff. Shiraz, are you going to share your screen? We're setting up. So we're very happy to have Shiraz Moonwala as the first speaker of the day, starting the theme for the day, which I think is going to be scattering. So Shiraz, the floor is yours. Just need to unmute yourself, Shiraz, when you're ready. Shiraz, I think you're still muted. There we
Yes,
go.
sorry.
There we go.
Yes. Undo. Sorry, just a minute. Okay. Thank you. Can you see my screen?
We can say fine, yes.
Okay. Okay. So thank you for the invitation, and thank you. It's great to participate at the first Zoom Strings meeting, and it's great that this new venture is in a new place. It's in Africa. The whole thing sounds very exciting. My talk today is titled "Constraining Tree-Level Gravitational Scattering," and it's based on two papers that have already appeared, and on some work in progress with these papers. Let me start my talk with a sort of provocative introduction. Consider type 2 string theory compactifications of the form Rp times M, where M is an internal manifold. For example, we could be in P equals 4 and M could be a Calabi-Yau manifold, or we could be in P equals 6 and M could be a K3 manifold. Now, any such compactification of string theory defines a quantum theory of gravity in Rp. At the loop level, gravitational scattering amplitudes that we get from string theory computations depend on manifold M in a sensitive way. For instance, the free loop or gravitational scattering amplitudes would be intricate functions of the moduli of the Calabi-Yau M. Now, in contrast, it's an obvious but nonetheless completely remarkable fact that this dependence on the detailed properties of this manifold M drops out at the classical level. That is, for tree-level. This fact is obvious. It follows immediately from the fact that graviton vertex operators lie entirely in the Rp part of the worldsheet conformity rather than some mix of Rp and M, coupled with the fact that the sphere regarded as a Riemann surface has no moduli. In fact, one can generalize the statement. The tree-level scattering amplitudes are essentially independent of M. They depend on it only in an overall factor. Pure partition function of the M. Same overall factor appears in all amplitudes. It goes into renormalizing the effect of Newton's factor. And these amplitudes are also the same for type 2A and type 2B theory, and also type 1 theory, comes to illustrate classical sphere amplitudes. The statements I made can be restated in a slightly more physical way from the point of view of spacetime. The spacetime implications of these worldsheet statements is that any compactification of string theory down to Rp times M admits a consistent truncation, classically admits a consistent truncation to a universal, by which I mean M-independent sector, which describes the interactions of an arbitrary number of gravitons, as well as a number of other fields, including spins of arbitrarily high speed. Okay, the important part here is that this sector is universal, independent of this manifold M, and so it's true of a wide variety of different theories, all of which have different quantum scattering. What I said for type 2 theory holds also for heterotic and bosonic compactifications. These also admit their own consistent truncations to their own universal sectors. Now, finally, there's another interesting classical gravitational S matrix that arises in string theory, but also outside. Interesting classical gravitational S matrix, which is the S matrix generated by tree-level graphs from Einstein. Now, as far as I'm aware, these examples exhaust the set of classical S matrices that reliably emerge in any parametric limit of string theory. The parametric limits relevant to the enumerated examples for the string theory scattering amplitudes are G-string taken to 0, with no restriction on the energy. And the parametric limits that lead to the Einstein S matrix in a wide variety of situations is by taking the energy to 0 with no restriction on G string. Now, the observations of the previous transparency motivate the following sort of bold conjecture. I'm going to call this conjecture 1 in this talk. Conjecture 1 states that classical Einstein S matrix, the tree-level type 2 S matrix, and the tree-level heterotic S matrices constitute the exhaustive list of consistent tree-level S matrices of gravity. Restated, every consistent classical theory of gravity admits a consistent truncation to one of the 3 universal sectors that we've talked about before: the universal sector of the type 2 theory, the heterotic theory, or in all that set gravity. Now, this conjecture has a number of words which need some explanation. What do I mean by tree-level S matrix? Well, that's sort of clear. What I mean by tree-level S matrix, at least what I mean by tree-level S matrix, is an S matrix which is analytic in momenta, is polynomials in momenta, apart from a bunch of singularities, and these singularities are precisely those that follow from the exchange of physical particles. So apart from taking away the singularities from the exchange of single particles, the pole singularities, the S matrix is polyanalytic. But consistent in the conjecture above, of course, is a bit vague. Part of the, and needs to be properly defined. But in particular, it means that the theory in question obeys the good properties we usually demand of classical theories, in particular causality, boundedness of energy, and perhaps more, perhaps unitarity when we quantize it in a set. Now, that something like conjecture 1 should hold has been suggested on several occasions by Nima Arkani Hamlet, certainly to me in private conversations. The conjecture 1 was validity or otherwise of conjecture 1 was also one of my 2 questions about gravity in the talk by that title that I gave in the 50th anniversary session of string theory. Okay. The observations of the previous transparency motivate. Now, conjecture 1 is a sort of crazy sounding conjecture, right? It's saying that it says that there's a huge degree of universality in classical gravitational scattering. Okay. However, conjecture 1 implies the following 2 successively weaker and perhaps less crazy statements. So one of the implications of conjecture 1 is conjecture 2, which is a claim that the only consistent tree-level gravitational S matrices with poles of bounded spin is the Einstein S matrix. Conjecture 2 clearly follows from conjecture 1, because conjecture 1 lists 3 possible general classical S matrices, 2 of which have poles of unbounded spin, so that leaves only the Einstein S matrix. And then an even weaker conjecture, something that's motivated by conjecture 2, but does not imply conjecture 2, is conjecture 3, which says that the only consistent tree-level S matrix with only gravitational poles, with no poles other than those coming from graviton, the Einsteins. So this is a sort of hierarchy of Russian dolls of conjectures. 1 implies 2 implies 3, but the reverse implications are. Now, in this talk, we will study aspects of the weaker conjectures 3 and 2. I will have nothing further to say about this absolutely fascinating conjecture 1, which sort of forms part of the scaffolding of motivational scaffolding for this talk, but plays no actual role in the talk. Okay, so let's start the more concrete part. Okay, I'm going to try to investigate these conjectures of uniqueness under certain conditions of gravitational scattering amplitudes. The conjectures are made for gravitational scattering amplitudes with arbitrary numbers of gravitons. The number of gravitons n here could be 3, 4, 5, 6. Now, the case n equals 3 is especially simple. This simplicity has its roots in the fact that the 3-graviton S matrix is very tightly constrained by kinematics. In particular, d greater than or equal to 5, any 3-graviton scattering amplitude is a linear combination of the one structure that comes from 2 derivative Einstein action, another structure that comes from 4 derivative Gauss-Bonnet action, and third structure that comes from 6 derivative Riemann cube term. I've listed the scattering amplitudes here. Note in particular that they are always polynomial in momentum. This is just kinematics, it's true, quantum mechanically, classically, whatever. There's some small detail that are different in d equals 4. So, this is what I've just said here. The most general 3-graviton S matrix takes the form A times T1, A times Einstein, plus B times Gauss-Bonnet, plus C times Riemann. Where A, B, and C are just numbers. They're not functions of momenta. So specifying 3-graviton scattering is just a matter of specifying 3 numbers. Now, Kamanov, Edelstein, Maldacen, and Zhibodev, in a remarkable paper written 6 or 7 years ago, demonstrated that any theory in which either B or C is non-zero is necessarily acausal unless it couples to higher spin particles of arbitrarily high spin. In other words, if you've got a theory that does not have particles, does not have exchange pole contributions from arbitrarily high spins, and it's causal, B and C must be 0. In other words, in any such theory, the theories that obey the constraint of conjectures, say conjecture 2, the 3-level graviton scattering amplitude is necessarily that of Einstein. In other words, C and Z have already established conjecture 2 at the level of 3 graviton scattering. This is very encouraging for these conjectures. However, note that 3 graviton scattering is scattering, as we've just reviewed. It's gives 3 numbers. 4 graviton scattering has qualitatively more complexity, and we can, the rest of the talk I will discuss scattering of 4 gravitons. Okay, so the context, the kind of S matrices of 4 gravitons I will study are those which are generated by local Lagrangians with a finite number of fields. All such S matrices are given by the sum of a finite number of exchange poles plus polynomials in momentum. Okay, take away the exchange poles, what's left is polynomials, perhaps a very high degree, but finite, bounded. The most general, so we're going to study both kinds of contributions one by one. Let's start with the pole contributions. The most general pole contribution is obtained by using, by sewing together 2 GG particle on-shell 3-point vertices through a propagator of the particle. It follows that a complete classification of GG particle 3-point couplings effectively gives you a complete classification of on-shell pole contributions to 4 graviton scattering. Now, GG particle couplings have been listed in special cases before. For instance, in P equals 4 for all representations are using Spinor helicity formalism. However, as far as we were able to, we were not able to locate a complete listing of these couplings in every dimension in full generality, so we just worked it out. So what we did was we gave a complete listing of first the full set of SOD-1 little group, massive SOD-1 little group representations that 2 gravitons can couple to. Second, the number of couplings, fix a representation, SOD-1 representations, 2 gravitons and that representations, how many different couplings are there. We counted the number of couplings. For any given representation, it's always a finite number, and in fact, this number is bounded. It's never larger than 8. Then we also gave a completely explicit basis for the structure of these SODs. Didn't just count them, we wrote them down. And we also listed a completely explicit basis for the local Lagrangians that generate these. Though we will not lead this in this talk, we also did the same for 2 photons and representation. Now, in a minute or so, I'll briefly outline the method we used to carry out this rather simple enumeration exercise. We've got 2 graviton scattering, and let's say the momenta K1 and K2. The momentum of our massive particles K1 plus K2 by momentum conservation. So the plane of momenta is 2-dimensional. The plane of vector spanned by the 3 momenta is a 2-dimensional plane, and we call this scattering plane. Now, a massive particle transforms in its little group representation of SOD-1, and it's the SOD-1 of rotations that stabilizes its momentum, namely K1 plus K2. Gravitational polarizations, on the other hand, transform representations of SOD-2, and the physical part of the gravitational polarizations can be shown to be tensor, a traceless symmetric tensor in the SOD-2 that stabilizes scattering. So a 2 graviton 1 particle S matrix is an SOD-2 invariant combination of the product of these 3 representations. These 3 representations are 2 symmetric traceless tensors of SOD-2, and this one SOD-1 representation, which descends into a finite number of SOD-2 representations. Okay, so we fuse the two graviton representations, and then Clebsch-Gordon them to get whatever we get, and then fuse those representations with what follows from the SOD minus 1 representation of the massive particle from descent. We also have to impose Bose symmetry. Anyway, all this is easy to do, and in doing that, we are able to produce a easy to do and easy to uplift to completely manifestly Cage invariant, Lorentz invariant S matrices. And in doing this, we're able to produce a very explicit list of these S matrices, these three particle S matrices. I won't, trouble you with the details. The thing that's important for me here is that when you go through this list, make the following observation. Every coupling on our list turns out to be a fourth or higher order in derivatives. Now, this fact has a simple physical interpretation. The physical interpretation is that the coupling between two gravitons and an additional particle, genuine couplings, interactions of two gravitons and additional particles, are always through two Riemann tensors and particle field, rather than something else, rather than, let's say, square root of G, that's the particle. Okay, since each Riemann tensor comes with two derivatives, 2 plus 2 is 4, so you never have less than 4. And now this might seem non-intuitive. For instance, you could have an interaction term like this, where a scalar multiplies R, or an interaction term like this, where some funny field in the same tensor with the same tensor representation as a Riemann tensor contracts with the Riemann tensor. And then you could expand either square root G, or you could expand R to quadratic order, and you would generate an H-H-S coupling, where H is the linear fluctuation of the graviton. However, these are fake couplings. Same Lagrangians, the Lagrangians I've written down here, also generate quadratic couplings of the schematic form HS. Now, if you want to be dealing with fields that create genuine particles, you want to do the field redefinition that diagonalizes properly. Once you do that field redefinition, it turns out that these three particle interactions also go away. The only genuine interactions, the ones that survive once you're working with properly normalized fields, the properly defined fields create actual particles, are those between two Riemann tensors and derivatives and this thing. That's basically what's going on here. That's why every interaction is a fourth or higher order. Now, the fact that it's fourth or higher order derivatives will enter in an important way later in my talk. Right now, there's already something that says that's interesting. This observation tells us that at least at the cubic level, at least as is relevant to 4 graviton scattering, any two derivative theory of any field coupled to gravity necessarily admits a consistent truncation to Einstein gravity. That is, in any two derivative action of some funny field coupling to Einstein gravity, there is never an exchange pole contribution to the 4 graviton scattering amplitude where that new field runs. This is crucial to conjecture to be at all a plausible conjecture. Because if you could make some nice, well-behaved two derivative theory and have it run in poles in 4 graviton scattering, then obviously Einstein scattering amplitude would not be unique. The fact that this never happens in two derivative theories gives you hope that conjecture two might be correct. Let me note that here we're using something that's really uniquely gravitational and doesn't apply to, say, the electromagnetic field. For instance, when you look at the scattering of 2 photons to a third object, it's easy to produce non-zero 3-point functions for that scattering amplitude at 2 derivative order. For instance, an axion phi with 2 f's, or a kiloton phi with 2 f's, produces a scattering amplitude from 2 photons to a scalar, which will appear in 3 scattering amplitudes. So something like conjecture 2 will not be true for photons, but could plausibly be true for atoms. Okay, so this is all I want to say at the moment for pole contributions to scattering amplitudes. Now I move on to the slightly more complicated polynomial contribution, classification of polynomial contributions to gravitons. So what do I mean by this? Most general, more or less by definition, the most general polynomial S matrix, polynomial contribution to graviton scattering, is the most general polynomial built out of polarizations of gravitons and momenta that have the following 4 properties. A, it's Lorentz, 1, it's Lorentz invariant, 2, it's separately quadratic in all polarizations because of gravities. 3, it's gauge invariant. 4, it's Bose-symmetric, that is, it's invariant under its 4 permutations. Okay, so what we want to do is to enumerate all polynomials that have these properties. In order to do this, it turns out to be convenient to first forget about this constraint to both symmetry. Just ignore it for a moment. Let's try to enumerate all the polynomials that satisfy the first three points. Okay. Now, suppose we've got some polynomial M that satisfies the first three properties. Some polynomial of polarizations and momenta, that's gauge invariant, Lorentz invariant, and has the right degrees in the polarizations. Now, it's completely obvious that if I take that object and I multiply it with any polynomial of Mandelstam invariance, this new combination also satisfies properties 1, 2, 3. Because the polynomial of Mandelstam invariance is obviously Lorentz invariant, it's obviously gauge invariant, and it is independent of the polarizations. This innocuous observation has a mathematical counterpart. In mathematics, this tells us the space of unsymmetrized polynomial S matrices, unsymmetrized meaning not yet S4 invariant, is a module over the ring of polynomials of Mandelstam invariance. Now, we got this nice module structure by completely ignoring S4 invariance. Actually, we can do it just a little bit better. Instead of completely ignoring S4 invariance, we can impose a part of it. We can impose invariance under a Z2 times Z2 subgroup of S4. This Z2 times Z2 subgroup of S4 is the subgroup generated by these subgroup consisting of these four permutation elements. What's special about the Z2 times Z2 is that it leaves the Mandelstam invariance ST and U unchanged. Easy to check. Now, suppose we look at the collection of polynomials of polarization and momenta that obey my old conditions 1, 2, 3. Gauge invariance, Lorentz invariance, appropriate homogeneity in polarizations. But in addition are also Z2 times Z2. Call this the space of quasi-invariant polynomial S matrices. Okay. And now, because ST and U are themselves Z2 times Z2 invariant, it continues to be true that if you've got one of these guys, a polynomial in ST and U, multiplying it is also one of these guys. And therefore, this structure, the structure of these quasi-invariant S matrices, is also a module over the ring of polynomials of ST and U. Okay. Now, this module is not exactly what we want. We want something that's completely invariant under S4. We still have to impose invariance under what's left over in S4 that's not in Z2 times Z2. So the quotient of S4 with Z2 times Z2, Z2 times Z2 happens to be a normal subgroup, so you take the quotient from either the left or the right to get the same thing, is the group S3. So the group S3 acts on this quasi-invariant module. And what we will later have to do is to impose invariance under S3 to get what we actually want. Okay, so we've got this nice, elegant mathematical structure of a module, and then eventually we have to project onto it in order to get a complete classification of allowed polynomial S matrices. Now, in general, a module is completely characterized by its generators. And if you don't really know what a module is, like I didn't know 6 months ago, just think of Virasoro primaries, okay? The modules that many physicists are familiar with in the structure of representations of conformal field. So the generator is like the Virasoro primary. So module is completely characterized by its generators, like its Virasoro primaries, and the generators of its relations. These are the null states. Okay, you specify all the primaries and all the null states, and you completely know everything you need to know about the module. Now, in our paper, we've explicitly listed both the generators and the null states when they exist of this quasi-primary S matrix module in every dimension, and so are completely characterized. Okay. With the module of quasi-invariant S matrices under complete control, it's a simple matter to enumerate the actual S matrices of interest, the ones that we're interested in, not just these guys that are Z2, Z2 invariant, but the ones that are more generally invariant and all of S4. This is simply the projection of this module onto the space of S3 sequence. And it's easy to do this projection. In the paper, we've done it and provided a completely explicit listing of all such S matrices, parity, even, parity, odd in every dimension. Part of the length of our paper is because the listings take so much space. We've also explicitly listed the Lagrangians that generate each of these S matrices. Okay, just as one quick example of just to show you that there are some results. You can count how many parameters there are in the S matrix at any derivative order. So, and arrange your information in terms of partition function. So this partition function here has the feature that if you extend it to a power series in x, then the coefficient of x to the power 48 tells you how many parameters there are in the polynomial for graviton S matrices at 48th element of order. We have these partition functions explicitly computed. We have similar results for photons, but I won't. Now, we're extremely consistent that our results are correct. We're extremely confident that our results are correct because we have a consistency check. We've obtained this partition function that I showed you on the previous page in one other way apart from using this module structure. What we did was to enumerate local Lagrangians up to field redefinitions and up to total derivatives. This enumeration scalar local Lagrangians up to field redefinitions and total derivatives. Such an enumeration should be in one-to-one correspondence with S matrices, but we did this enumeration in a completely different way. What we did was we took 4 graviton partition functions and then projected it onto the space of SOD singlets by doing a Haar-Measure integral after removing total derivatives. The computation is not completely trivial, but we managed to carry it through. And when all the dust settles, both methods give exactly the same results, giving a highly non-trivial check of our modular structure. So we're pretty sure we control the structure of these S matrices very, very completely. Good. So far, this talk has just been about kinematics. Okay, we've now reached the stage that C, M, Z were at when they were trying to constrain three graviton scattering amplitudes. When we've reached the stage where they were at like the first page of their paper, where they said shared with 3 graviton scattering amplitudes, A times Einstein plus B times Gauss-Bonnet plus C times Riemann. Now what we need to do is to do some physics. Okay, we need some physical requirement to cut down this huge space of possibly kinematically allowed S matrices. Okay, and that's what we're heading towards. So what we're going to do is to use a principle which is motivated by holography and chaos bound. So let me give you a brief review. Recall that Maldacena, Schenker, and Stanford demonstrated the following fact. Take any conformal field theory and view it in the XT plane. Okay, and look at a four operator insertions in this XT plane. The 4 operators are inserted in the following way. First, you insert an operator at t equals 0, x equals 1, and then boost this operator with boost parameter e to the power tau by 2. Then put an operator in the same place and boost it with e to the power minus tau by 2. And then repeat the whole thing by inserting the operator at x equals minus 1 t equals 0, and then boosting with the same 2 boosts. So now we have 4 locations for operators. Maldacena, Schenker, and Strominger, Maldacena, Schenker, and Stanford worked in the limit n goes to infinity, and then tau goes to infinity. They first took n to infinity, then took tau to infinity, and demonstrated that while this 4-point function was allowed to grow, it was not allowed to grow faster than e to the power tau. What we're going to try to do is to use this constraint to try to constrain possible bulk duals of holographic field theories and tease out from there possible general principle constraining bulk interactions. Okay, so to start with, let's take an example. Suppose we've got a situation with holographic dual to our field theory has a scalar field with local Lagrangian and perhaps more general couplings that would generate a local S matrix, perhaps. Now, such S matrices can be parametrized in a manner very similar to what I described for the gravitons, except it's much easier. It's a trivial exercise. Hinchcock, Penedor, Pulchinsky, and Sully used the usual ADX CFT dictionary to explicitly construct the boundary 4-point function that arises out of any given bulk S matrix. It's a relatively simple matter. You so with the diagrams and do some integrals. Now, using their results, one can verify the following. Consider a term bulk Lagrangian that would lead to a fast path-based S matrix that scales in the Regge limit. The Regge limit is large S and fixed t, like s to the power m plus 1. The 4-point function, the boundary 4-point function that follows from the same bulk interaction term in this chaos limit turns out to scale like e to the power m times tau. Yeah. Okay. Now, it follows immediately that any local bulk term that leads to an S matrix that goes faster than S square would give rise to a boundary 4-point function that violates the chaos bound. This suggests that all bulk interactions that lead to S matrices that grow faster than S square are unphysical. This observation leads us to make the following conjecture, which we call the classical Regge growth conjecture. Classical theory says S matrices grow faster than S square, and the Regge limit is unphysical. That something like the CRG conjecture should be true has been suggested sometimes implicitly by many people, including in appendix of the CMZ paper, by Maldacena, Schenker and Stanford, by Karen Ho, by Zhibanev, by Arkhani Ahmed, and many others have shown. Now, the sharp link between the CRG conjecture and chaos bound has so far been most clearly established for scalars. In a project I'm making with my collaborators, we are carefully verifying that this tight connection holds also for spinning particles. The work is not complete, but the results are so far encouraging. Okay. As further weak evidence for the CRG conjecture, note that it's A, saturated in Einstein gravity, and B, obeyed in string theory, because string scattering amplitudes grow like S to the power 2 plus positive number times T. T is negative when in physical scattering, so the S power goes below 2 rather than above 2. Okay, great. So now we have a principle, the CRG conjecture. We can now marry this physics principle with our painstakingly constructed parameterization of allowed local S matrices to see which of these allowed local S matrices survive our physical cut. Just by explicitly, I'm going to first discuss the polynomial S matrices, then we'll turn to the poles. Just by explicitly running through our list of polynomial S matrices and allowing for all possible linear combinations, it's very easy to check that there's exactly one S matrix, one polynomial S matrix that is CRG allowed. It goes no faster than S square in the fixed T limit. And this is the S matrix that I've displayed here. It's given by a wedge product of polarizations and momenta squared. Okay, this is 6 derivative S matrix, which roughly speaking scales like STU. And so CRG allowed, because in the Regge limit, U and S both scale like S, T is held fixed, so it scales like S squared. This S matrix follows from the following Lagrangian, which is familiar to people who study classical, modified classical gravity. This Lagrangian is the second Lovelock. First Lovelock is Hausberg, which is the same. Okay, so let's summarize. What we demonstrated already is that the most general, purely gravitational CRG allowed action, up to terms that cannot affect 4 graviton scattering. Riemann to the 5 and so on, we ignore it. We say, have nothing to say about it. But including only terms that can affect 4 graviton scattering, is A times Einstein plus B times Gauss-Bonnet plus C times Riemann Q plus D times this chi-6, where chi-6 is this funny second Lovelock action. Now look again at chi-6. Chi-6 involves the anti-symmetrization of 6 indices. So it's obvious that this chi-6 identically vanishes for D less than 2. It's perhaps less obvious that what's perhaps less obvious is that in D equals 6 it effectively vanishes, in that it turns out to be a total divergence. Okay, this is clear from the form of the S matrix. It's a wedge product of 7 objects, and so vanishes. Okay, so this I6 is only something you can non-trivially write down in 7 and higher dimensions. So if we're at D less than equal to 6, the only allowed purely gravitational terms that contribute to gravitational scattering are A times Einstein plus B times Gauss-Bonnet times C times Riemann. Okay, nothing else. No Riemann to the 4 term, nothing else that could affect 4 graviton scattering is allowed if you buy the CRG conjecture.
Sure, as you have about 5 minutes.
Yes.
Yeah.
So far, we have considered the implications of the CRG conjecture and polynomial contributions to 4 graviton scattering. But as we've already discussed above, the most general contribution also has exchange pole contributions. Now, let's first look at the contributions, exchange contributions due to graviton. Okay. These amplitudes can be thought of as a bilinear form in these 3 variables A, B, and C, because you've got a 3-point function on one side, a 3-point function on the other side, you put a graviton pole in the middle, and so together, so it's quadratic in the areas. Okay. Now, one of the things we did in our paper was just explicitly construct this 4-point, this bilinear form. Just construct the most general 4-graviton, compute the most general 4-graviton S matrix that came from graviton exchange, and we just explicitly check that that this exchange contribution violates the CRG conjecture unless B is equal to C is equal to 0. So this tells us that the CRG conjecture tells us that B and C, at least in the purely gravitational part, if it's not cancelled by anything else and so on, B and C must be 0, and at least in D less than or equal to X focuses on purely the Einstein result. Notice in particular the CRG conjecture implies the CMZ result, but it implies much more because it rules out all these infinite number of R to the 4 terms, all the polynomial things. Now, a quick aside. In the last slide, I claimed that the exchange contributions from, for instance, let's say if you sew together 2 Gauss-Bonnet matrices, it goes faster than S squared. Sometimes this causes confusion because people quote results that exchange contributions from particles with spins, particles of spins J cannot grow faster than S to the J. And since we're only exchanging gravitons, how can this possibly grow faster than S squared? It turns out that the statements that exchange contributions cannot grow faster than S to the power J is correct in the T channel. It's not true in the S and the U channel. Okay, and the CRG scaling for 2 Gauss-Bonnets gets violated in the S and the U channel. It gets violated in a way that is polynomial. The violation term, the term that scales faster than CRG allowed, is polynomial in T, and so it's local in impact parameter space. So it's not a violation that you would see if you were staying, finite distance, finite impact parameter away. It's a purely local kind of violation. This is the kind of thing that's going on. Makes it consistent with 6 to the power J, S to the power J integers. Okay. Now, so far we've only looked at graviton exchange, but we can now move to looking at the most general massive exchange. Using the fact that we carefully verified early in this talk that G particle couplings always involve 4 derivatives or more, in our paper we presented a general argument that all massive exchange contributions to 4-graviton scattering go faster than S squared, at least for D less than or equal to 6. And that this growth is of a form that cannot be cancelled by a local commutator. It's not like this growth plus some local term together grow in a CRG acceptable way. Moreover, however, of course, two exchange contributions, just kinematically, 2 exchange contributions could cancel each other, leading to CRG allowed growth. However, there's another principle that forbids this. It's in the exchange contributions, unlike contact contributions, always come with a definite sign, because the propagators that we that requirement comes from the fact that coupling constants are real. The propagators have a definite sign. So when we put in the condition that the exchange contributions always are of the right sign, different exchange contributions can only add up. We can't cancel each other. Okay. So the end result of this analysis is that there is, at least in D less than or equal to 6, there is no single or finite number of exchange contributions of massive particles that does not violate the CRG conjecture. Okay. So assuming the CRG conjecture, we're very close to a proof of conjecture 2 for when we're in G less than or equal to 6, at least for the special case of 4-graviton, for the special case of 4-graviton. Yeah. Okay, so I'm more or less done. So let me end with my discussion of the conclusions. Let me remind you, in this talk, I presented a complete classification of 4-graviton and 4-photon classical scattering S matrices in a theory whose Lagrangian has a finite number of derivatives and a finite number of fields. I've then presented a conjecture about the allowed growth of S matrices in classical theories. I've used this conjecture to completely classify all allowed classical theories of gravity up to terms that don't affect 4-graviton scattering. This classification is particularly tight at D less than 6, where we're down to basically Einstein. The many things remain to be done. It would be very nice to understand the S-squared conjecture better, and to turn it from a conjecture to a result, to prove it directly in flat space without appealing to the chaos bound, without appealing to ADSC. It would also be interesting to understand if the status of the ambiguity in D greater than or equal to 7. Is this a genuine ambiguity? Or is the coefficient of this chi6 set to 0 by some other physical consideration? we have not yet accessed. Using the ADS-CFT correspondence, our results are closely related to results for TTTT 4-point correlators, or stress tensor correlators in large N conformal field theories. In particular, our results are basically the statement that there is only large N TTTT 4-point correlator of stress tensors, which receives contributions only from double trace exchange, arbitrary double trace exchange, and finite number of single trace exchange. But the only correlator of this form actually receives contributions from no single trace exchange other than the stress tensor itself, and is in fact the correlation function from generated by Einstein gravity. It would be very interesting to generalize the results of Stokes to scattering of more than 4 gravitons. Many ways one could go about this. Perhaps it would be nice as a starting point to have something like the chaos bound for 6 insertions. Finally, if all of this works out and there are no bugs along the way and no surprises, we can then get more ambitious and try to generalize the study of Stokes beyond these local S matrices with finite numbers of fields, with the hope of establishing conjecture 1, which is basically the uniqueness of string scattering amplitudes or something like it. Thank you.
So thank you very much, Shiraz, for that. Waiting for the applause. So we have a number of questions. Enrico, I think you were the first one to put your hand up. So please go ahead, Enrico.
Yeah, thank you very much. Thanks for the nice talk, Shiraz. One question is about the assumption, which is crucial in this discussion, that Lorentz symmetry is respected by the ground state of the theory and therefore is linearly realized and plays a strong role. Nevertheless, in most physical systems, Lorentz symmetry is not a symmetry of the ground state. And I'm thinking, for example, at all condensed matter system, but perhaps more relevantly in the gravitational context at cosmology, there is a preferred frame in our universe. And so Lorentz boosts are typically non-linearly realized. Now, yes. in this setup, there are many more cubic graviton amplitudes that are allowed by the symmetry. Just you could think of, I don't know, gamma dot cube or something else which is not Lorentz invariant. This is, on the one hand, yeah, theoretical is a possibility. On the other, it's also observationally very important, because one hope that we have to measure the 3 graviton amplitudes is if in some distant future we measure from inflation the tensor perturbation, we will see the 3-point function of the graviton, and that is in the cosmological setting, so in a setting in which Lorentz boosts are broken. Now, given that, do you have some thoughts on how much we could say about cases in which Lorentz symmetry is not linearly realized, and how much we could try to have a classification or some general rules that are valid in that case as well?
Yeah, my guess is that everything would become much, much weaker in that situation. Let me explain why my way of thinking. As I sort of explained at the beginning of my talk, you know, the apparent near uniqueness of string scattering amplitudes is a limited statement. It's a statement that applies only to the consistent truncation, a particular consistent truncation that involves the graviton and a bunch of other fields, and does not imply, of course, scattering amplitudes of fields that lie outside this consistent truncation. So, for instance, if you're scattering some moduli field of your Calabi-Yau, of course, the answer to that depends on which Calabi-Yau you're at, where in the moduli space you're at. The important thing was that in flat space, okay, there was this consistent truncation. So though these other fields existed, they were never produced if you just scattered 2 gravitons. Now, if you turn on a more general background of string theory, one that does not, where the background itself does not lie within this consistent truncation, but it's a background that involves fields from the non-universal part of the theory, okay, then all bets are off. Everything will start getting less and less unique. At least something like conjecture 1 will certainly start being violated that way. And these backgrounds have the spirit of nonlinear realizations of Lorentz invariance. So I feel that, you know, even the motivational universality for these amplitudes somehow very tightly connected to the consistent truncation that appears in flat space. So I would need to think harder about your precise question to say something more. more serious.
Okay, yeah, thanks a lot. That's very interesting. I think there is good reason to think about that question as well because of practical relevance. But thanks a lot for your thoughts.
Thank you.
All right, thank you. The next question comes from Guillaume.
Hi, Shiraz. I was wondering if you add maybe a few more hypotheses, if you can have a spin one version of the conjectures, because your counterexample of 2 photons and 1 scalar, maybe it exists because the particles don't carry electric charge. But what if you had, like, I don't know, like gluons and charged matter? Do you think that there would be a version of these conjectures in that case?
Gluons and charged. Yeah. So your point is that charged matter has to couple sort of quadratically.
Right.
Yes, it could well be that, well, it's not, yeah. It could well be that if you make more specific assumptions, yeah, I think that what you're saying is this. If you are in a situation where there is a symmetry that imposes a consistent truncation, then that will, of course, be exact. And your gluons with charged matter would be that kind of situation.
Right.
Right. So, again, I would have to think harder, but I think it's plausible that if you impose further conditions, there would be more one could say. Yeah.
All right, thank you.
Okay, thank you. Next question comes from Andy Strominger. Andy?
Beautiful talk. I want to ask, I'm fascinated by this relationship between the chaos bound and the conjectured Reggie growth. And I'm wondering if you could say something about, in that discussion, what's perturbative and what's non-perturbative, and what's classical and what's full quantum. So the conjecture Reggie growth, I understand, is a statement about classical terms in the perturbative terms in the S matrix, but the chaos bound, as I understood, would be, why don't you have to sum the whole series, which could change the behavior and also include logs and quantum effects? What?
So the chaos bound is a statement about the growth of correlation functions at leading order and large n. Like, if you first take the large n limit, and then you look at the growth.
Yeah.
Okay. So that maps to a classical statement on the bulk side, because large n limit is like classical limit on the bulk side. However, there is something interesting here. Because you see, chaos bound was even a meaningful statement because there was, there is a simpler bound than the chaos bound, the bound that they start the chaos bound paper with, namely just a Cauchy-Schwarz inequality. Okay, an inequality that tells you that some correlation function in some units cannot become larger than 1. Now, in large n theories, that correlation function sort of starts out very small and then starts approaching 1. And that rate of approach to that is bounded by this e to the power tau growth. But the fact that it cannot ever exceed 1 is a more elementary bound. That should, in some sense, presumably lead to bound on growth for also quantum S matrices, which, if my analogy is right, should be even tighter than this classical Reggie growth. It would naively suggest that there's some bound for quantum S matrices that is sub S square. It's like the classical limit helps you violate something, quantum mechanically would become tighter. This would be my guess.
But why don't we have to resum the whole series?
In order,
I mean, it could grow like S squared, then it could violate S squared, and then you resum the series, it could die exponentially.
Resum the series in the
resum the perturbation series.
The perturbation series, right. So there will be some value. So you start growing. Then at some point, it might be that your higher order corrections kick in, and change this S square growth. But that happens at some very large value of S square. So what we've got is a window where you can ignore all the quantum corrections. Okay, and in that window, it cannot grow faster than S square. Then what happens once quantum corrections kick in? That's more complicated. That's the regime where I believe the S square bound will actually be tapered off from S square to S. But we could just work in the limit where we first take G string to 0. So the classical thing is reliable. However, that might start becoming unreliable as we go to higher and higher energy. So there will be some energy where that's no longer valid, at which point you need to work. It's very similar to the chaos bound. We first take n to infinity. You could also ask there, what happens when you resum the 1 by n? It's a very similar discussion.
Thank you.
Okay, thank you very much. I don't see any more questions, any more hands raised at the moment. So I suggest we thank Shiraz again, and then we will break for about 5 minutes before Andrea's talk. Anyone who wants to carry on the discussion, just a reminder that there's a Slack channel and you can join the channel for Shiraz's talk and continue the discussion there. Thank you. Are you ready to begin, Andrea?
Yes.
Okay, great. So we're very happy to have Andrea to talk about asymptotic symmetries and celestial CFT. Please go ahead.
Thanks a lot for the invitation to speak, and many thanks to Jeff and all the other organizers for making this event possible virtually. It would have been a great pleasure, of course, to be in Cape Town physically for both Strings 2020 and Ropes 2020. But it is a great consolidation prize to have this event come online, which has allowed so many more participants to come together. So my talk will be in the context of recent attempts at flat space holography, with focus on the asymptotic symmetries of asymptotically flat space and how they manifest themselves in a proposed dual celestial CFT. The results that I'm going to present will be largely based on a paper that came out in May, which were done in collaboration with Laura Donnet, who is a postdoc at TU Vienna, and Sabrina Bastersky, who is a postdoc in Princeton. It will also build on earlier work, including a paper with Laura and Andy Strominger from a little over 2 years ago, which has brought me to this topic. So I think it is fair to say that most of our recent understanding of quantum gravity comes from the holographic principle applied to enter de Sitter space, where the gravitational and stringy bulk physics has a dual description in terms of a conformal field theory living at the boundary of enter de Sitter space. Underlying this powerful duality is the identification of the symmetries of enter de Sitter space with those of a proposed holographic dual boundary theory, and the match of the degrees of freedom, which is beautifully exemplified by the explanation of the black hole entropy from the dual CFT. Now, one of the distinguishing features of enter de Sitter space is, of course, its confining boundary conditions, which lead to the slogan that we can study quantum gravity in a box. Now, the spacetime near highly charged or highly rotating black holes is well described by enter de Sitter space, but vast regions of our universe are not. So at the cosmological scales, we should, for example, rather use de Sitter space, while there are many scales in between for which Minkowski space is a good approximation, at least away from sources. So it begs the question how generally applicable the holographic principle is. And in particular, can the four-dimensional space-time physics in asymptotically flat space be encoded in some dual boundary theory that lives perhaps at the conformal boundary of Minkowski space? Now, any attempt at such a flat space holography has to answer a set of fundamental questions, and some of these include: what are the symmetries of the space-time? Can they be identified with those of a dual boundary theory? Is this dual boundary theory a conformal field theory? What are its properties? And so on. Related to this set of questions is the realization that there exists a conformal basis for quantum field theory scattering amplitudes. And this arises because the four-dimensional Lorentz group acts on the celestial sphere at null infinity as the global conformal group. And this means that four-dimensional scattering amplitudes can be recast in terms of two-dimensional correlation functions. Now, the study of this conformal basis might give us powerful constraints on the quantum gravity S matrix, as well as provide new insights into hidden structures and symmetries of amplitudes. In this talk, I will like to study and discuss a unified treatment of so-called soft modes in this new conformal basis with a view towards flat space holography. In particular, I would like to discuss the spectrum of two-dimensional primaries in this putative celestial CFT. I will discuss the symplectic pairing of so-called conformal primary wave functions, which is important for understanding the soft sector of the theory. And I will give an example of a celestial analog of quantum field theory soft theorems. Now, this discussion feeds into a question that any attempt at flat space holography has to answer. And this question is, what is the asymptotic symmetry group of Einstein gravity at null infinity? This is, of course, an old question, but we will look at it from a new angle, namely from this angle of having a new conformal basis at our disposal. And this will allow us to identify certain gravitational modes in this new basis with the generators of asymptotic symmetries. This consists of the BNS group, as well as a celestial conformal symmetry group. Now, the latter comes in the form of two distinct proposals, one being the Virasoro symmetry group generated by local conformal Killing vectors, and the other being a more general diffeomorphism symmetry on the celestial sphere. Now, there are important differences between these two proposals, and there are subtleties, and I will discuss them in the context of this conformal basis, which will shed new light on these subtleties. So the discussion of flat space holography should probably start with the Penrose diagram of Minkowski space. Here are highlighted in blue the conformal boundary of Minkowski space given by null infinity, which is a natural place where a dual boundary theory would live. So this is the place where massless particles enter the spacetime and exit it. Of course, massive particles start out at the bottom here at past time like infinity and end up at the future at the top at future time like infinity. A convenient coordinate system that describes the physics near null infinity, near this conformal boundary, is given by Bondi coordinates. This consists of a radial coordinate r, a set of complex angle coordinates z and z bar, which denote the angles on the two-sphere, and retarded time for parameterizing future null infinity, and advanced time v for parameterizing past null infinity. Now, in this two-dimensional diagram, I have, of course, omitted the two-sphere. So this is given by a pair of points, one on the left and one on the right with respect to the origin, which is given by this straight line here. Pushed to infinity, this two-sphere is then the celestial sphere. Now, scattering amplitudes in Minkowski space have to obey Lorentz symmetry, and this acts as the two-dimensional celestial sphere as the global conformal symmetry group. So the four-dimensional S matrix, which is labeled by the energy, the momenta, and the helicities of the external particles, can in this way be recast as a two-dimensional correlation function, where operators are inserted at points z, z bar on the celestial sphere and are labeled by the quantum numbers under the conformal group, namely the conformal dimension delta and the spin j. Underlying this equivalence is a change from the usual momentum basis that makes translation symmetry manifest to a new basis that makes conformal symmetry manifest. This basis change is achieved by an integral transform called a Mellin transform, which in this context is given by an integral over the energies from 0 to infinity with this factor energy to the power delta minus 1. The momenta get now replaced by the points on the celestial sphere where particles enter and exit, and the helicities under this map get identified with the 2D spin. The notion of energy now gets replaced by the introduction of the conformal dimension delta via this integral transform. Plane waves with energy omega and momentum p, or equivalently null vector q, get now mapped to boost eigenstates, which are given by 1 over the null vector dotted into the spacetime vector to the power delta. A basis of finite energy wave functions is now mapped to a basis of new wave functions. And these wave functions have the property that the conformal dimension lies on the principal continuous series of the Lorentz group. So in order to have a complete delta function normalizable basis, the condition on delta is that its real part has to be 1 and its imaginary part is a real number. Now, the interesting property of these new wave functions is that they transform as conformal primaries under the conformal group with weights h and h bar. The Mellin transform of these plane wave functions gives rise to scalar conformal primaries, while by adding suitable polarization vectors and tensors, we can get wave functions that are gauge equivalent to spin 1 conformal primaries and to spin 2 conformal primaries. So under this map, we have an identification of massless particles with these conformal primary wave functions. Now moving on from wave functions to amplitudes, we can now Mellin transform each of the external particles in an amplitude, and in this way obtain a celestial amplitude, which, as already mentioned, takes the form of a two-dimensional correlator. Now, as an example, let's consider Young-Mills theory and look at the 4 gluon amplitude given on the left. A Mellin transform of each of the 4 external particles will take it to a celestial amplitude, which we recognize as a 4-point correlator in the two-dimensional CFD. Z here is given by the conformal cross ratio, and this universal factor here is given in terms of the distance of points Zi minus Zj on the celestial sphere. Now, what's less familiar in this correlator is the appearance of these delta functions. And this hints at a more exotic nature of this putative celestial CFD. Now, what about the spectrum? So finite energy wave functions get mapped to conformal primary wave functions on the principal continuous series. And this map involves integrating over all the energies. So what is immediately clear from this integral transform is that the notion of an energetically soft particle, namely one where its energy is taken to 0, gets lost in this transform. But this limit is an important limit in quantum field theory scattering amplitudes that tells us about universal factorization properties. And surely universal properties of amplitudes should not be lost under a simple basis change. So something should take its place. So what we proposed was that instead of the conformally soft limit, in this new conformal basis, one should take the conformally soft limit. So this corresponds to taking the weights, h or h bar under the conformal group, to 0. But actually there's a bigger story here, which is that the orders of omega in an energetically soft expansion of the amplitude gets now mapped to poles in the conformal dimension of the corresponding 2D correlator. And the poles arise at certain integer values of the conformal dimension delta. So while, for example, for Yang-Mills theory, the conformally soft limit, which would agree with taking h or h bar to 0, would correspond to taking delta to 1. For these other conformally soft limits, this takes us off the principal continuous series. And this immediately raises a question, namely, how are these conformally soft modes consistent with the statement that conformal primary wave functions on the principal continuous series form a complete basis? Now, this tension is only apparent and can be resolved by studying in more detail the conformal primary wave functions and the Mellin transform and its inverse. And I will do this now for gravity. So we start again with the Mellin transform of a plane wave of spin 2, which is labeled by the conformal dimension delta and the spin. From now on, I will denote the spin by this two-dimensional index A. If it takes the value WW, this corresponds to spin plus 2. And if it is W bar, this corresponds to spin minus 2. The plus minus label here denotes whether the wave is outgoing or incoming and is in correspondence with a plus minus I epsilon prescription of the 0 of this denominator here, which happens along the light sheet. Now, this wave functions is not yet a conformal primary, but can be made into one by adding a total derivative term. And this total derivative term is given by this diffeomorphism zeta delta. Now, I would like to emphasize that this diffeomorphism is not just a trivial diffeomorphism that denotes a redundancy of the theory, but actually for the conformally soft limits that we'll be interested in, this corresponds to a large diffeo, a large gauge transformation that changes the physical state at the boundary. So now these objects H delta form a basis of conformal primary wave functions of spin 2 with conformal dimension on the principal continuous series. And now, while I'm at it, let me also introduce another interesting integral transform, which is called the shadow transform, which will be useful in the following. So this is a transform that takes an operator of dimension delta to an operator of dimension 2 minus delta, or delta tilde for short, and flips its spin. Okay, now the statement is that conformal primary wave functions of arbitrary conformal dimension delta, written here on the left, can be obtained from a certain contour integral of principal series wave functions denoted by HS on the right. So in this contour integral, there's this boldface delta denoted in red, and this corresponds to a regulated version of a distribution that is generalized to the complex plane. When the real part of delta lies on the principal series, so on this contour, then this distribution just reduces to the ordinary Dirac delta function, and this equality is just trivial. When the real part of delta lies to the left or to the right of the principal series, then we can use a regulated version of this distribution, which is given by the Mellin transform of an exponential. And that has the well-known result that it's given by the gamma function. And nu here is a regulator that will take to 0 in the end. So now when we plug in this expression into this contour integral, it's immediately clear what we have to do. So we can close the contour either to the left or to the right, depending on where it converges, and then use the residue theorem to pick up the poles of the gamma function. In this way, we will validate the statement that conformal primaries with arbitrary delta can be expressed in terms of principal series wave functions. And so this resolves the tension that the conformally soft limit in the spaces given by certain integer values of delta does not augment the principal series basis, but instead these wave functions can be obtained from a certain superposition of principal series wave functions. Okay, with that understood, it is now natural to expand a general metric perturbation H in this conformal basis purely in terms of principal series wave functions. So these are given in blue here. In red are the creation and annihilation operators, and these curly ends here are normalization factors that give us the canonical commutation relations for A and A dagger. Now I would like to introduce a mode operator, Q delta, with respect to a suitable inner product, which is denoted by these round brackets here, and evaluate it on some Cauchy slice sigma. This mode operator has the property that it shifts the metric according to this expression. And when acting with it on the vacuum, it produces single particle states with this profile H delta. Now the notation here is not accidental. These modes Q delta will actually correspond to charges. And in particular, when we take the conformal soft limit of taking delta to 1 or to 0, these Qs will correspond to asymptotic soft charges at null infinity once we take this Cauchy slice to null infinity. And this brings me to the discussion of the asymptotic symmetry group, which starts with imposing boundary conditions. So in a radiative spacetime, we have to add to the exactly flat Minkowski metric extra terms, and these extra terms are characterized by the free data. So this is a 1 over R expansion, and there are functions of the angles and the retarded or advanced time, and these are given by these 3 terms. So this is the Bondi mass aspect, the angular momentum aspect, and the gravitational data. And these are related by the constraint equation, but otherwise an arbitrary function of the angles. Of particular importance will be the change of the gravitational data with respect to retarded time. And this expression defines the Bondi-News tensor. So this is in a sense a dynamical graviton mode. Now the asymptotic symmetry group is then defined as the set of allowed gauge transformations that respect the chosen boundary conditions, modded out by the trivial ones. And by trivial ones, I mean gauge transformation that vanish at the boundary and denote the redundancy of the theory. Now, what is the asymptotic symmetry group of asymptotically flat space? Well, the most naive guess is that it should be the Poincaré group. After all, fields grow weak far away and the curvatures are low. So what else could it be? But however, what has been found instead was that the translations of the Lorentz group, of the Poincaré group, get instead locally enhanced. And this leads us to the so-called BMS group, which is given by the boundary conditions as written here. So there are order 1 over R, order 1, and order R contributions to the metric. And I have explicitly written out the order R contribution to the angular piece of the metric, which is given by the gravitational data. And this will be the key player in the following. So now asking what gauge transformations respect these boundary conditions lands us at the following diffeomorphism vector field zeta. So this is given in terms of a function f, which is an arbitrary function of the angles. The action of this diffeomorphism on the metric, and in particular on the free gravitational data, is given by this expression here, where the blue term highlighted here corresponds to an inhomogeneous shift. For the ZZ component of the gravitational data, this inhomogeneous shift is simply given by 2 covariant derivatives acting on this function f. The physical effect of this diffeomorphism is now that the global translations get enhanced to angle-dependent supertranslations that are characterized by this function f. In other words, global energy conservation now becomes a statement that energy is conserved at every angle. And so by allowing for these diffeomorphism vector fields, the Poincaré group gets enhanced to the BMS group. BMS supertranslations are related to other gravitational infrared effects. These are the gravitational displacement memory, which was first studied in the 70s, and Weinberg's soft graviton theorem, which was studied in the mid-60s. Now, I would like, if asymptotically flat space is holographic, then we should be able to describe these effects purely in terms of 2-dimensional language. And this is what I want to turn to next. So I already hinted that the conformally soft limit is given by taking the conformal dimension to certain integer values, and these integer values start at 1. In that limit, the conformal primary spin-2 wave function reduces to a total derivative. And the effect of this diffeomorphism vector field zeta is that it changes the physical state at the boundary. And this change is given in terms of a function f, that's a specific function of the angles, which is denoted here for a positive helicity graviton, as indicated by this WW here. Now we recognize that this physical change of the boundary state corresponds precisely to the effect that a BMS supertranslation has. So this delta equals 1 primary mode corresponds to the Goldstone mode of spontaneously broken BMS symmetry. One can compute a soft charge or define a soft charge for this BMS symmetry. And this is given by this expression in the box, where the blue term corresponds to this inhomogeneous shift, while the red term corresponds to the bond-induced tensor of the background. Now, in this limit of delta going to 1, there is an immediate puzzle that presents itself. And this is as follows. So in the conformal basis, primary wave functions are paired. And in particular, they are paired with respect to some suitable inner product. They are paired between wave functions with dimension 1 plus I lambda and 1 minus I lambda. Now in the limit where lambda goes to 0, or equivalently delta goes to 1, it is not obvious what the symplectic or canonical partner with respect to such an inner product what the symplectic partner for this dimension 1 Goldstone mode should be. And moreover, these shadow primaries that I introduced before, when the dimension of those is also taken to 1, these correspond to total derivative terms as well, and moreover coincide precisely with the dimension 1 Goldstone mode. In the momentum basis, the partner of this Goldstone mode is the soft graviton. And this is obviously important for the soft graviton theorem and for gravitational memory. However, in this new conformal basis, after performing the Mellin transform, it is very subtle to see where this symplectic partner of the dimension 1 Goldstone mode is, or equivalently, what the celestial analog of the soft graviton is. One way to understand where this partner comes from is by realizing that there exists a logarithmic branch of the solution space, which is not captured by the Mellin transform of a plane wave, naively. So this is obtained by taking a combination of primaries with dimension delta and their shadows, taking a derivative with respect to the conformal dimension, and then taking the conformal dimension to 1. So this is a quantity that remains finite in the conformally soft limit, and it does not correspond to a total derivative. So this comes with in and outgoing modes. And when taking a certain combination of in and out modes that does not decouple in scattering amplitudes, we arrive at the new conformal primary, which is the celestial analog of the soft graviton. So this dimension 1 conformally soft graviton is given by this distributional expression, and it can be visualized as a gravitational shock wave that has support along and outside the light cone of the origin. Now one can explicitly check that this new conformally soft graviton mode is the symplectic partner of the dimension 1 Goldstone mode. And so in this sense, we've understood that there is a symplectically paired set of zero modes, where one of the modes is not trivially visible in the conformal basis after performing the Mellin transform. Now, starting from this mode operator that I introduced earlier, we can construct a descendant which has conformal weights 3½ and 1/2. So this is a curious object. And this descendant in the conformally soft limit when delta is taken to 1 turns out to correspond to the BMS supertranslation current. So this is the generator of BMS supertranslation symmetry. Now one can ask what happens when this BMS supertranslation current is inserted into amplitudes. And let me start by discussing the momentum space version, which is Weinberg's soft graviton theorem. So when the energy of an external graviton is taken to 0, then the amplitude factorizes into a lower point amplitude without the graviton and the soft factor that corresponds to a pole in the energy. To project out this pole, we can start from the amplitude multiplied by the energy of the nth particle and then take this energy to 0. In this way, we get a factorization of the lower point amplitude and a soft factor. And the soft factor has a dependence on the momenta, or equivalently on the points on the celestial sphere where particles enter and exit. and explicit appearance of this factor of the energy of the kth particle. And then there's a sum over all the n-1 remaining particles. Now, the explicit appearance of this energy here can be understood from the OPE of the operator with that energy and the supertranslation current. So this funny looking OPE with the supertranslation current gives an explicit factor of the energy. And this is very important when trying to understand the celestial analog of soft theorems. So here, instead of the energetically soft limit, we should take the conformal soft limit of delta going to 1. And the first thing to notice is that the explicit appearance of this factor of energy in the OPE with the supertranslation current gets mapped to a shift in the conformal dimension of the operator in the conformal basis. And this means that the conformal soft graviton theorem in this new basis has now the lower point amplitudes has a shift in the kth conformal dimension in the lower point amplitudes. So the momentum space factorization is not exactly mimicked in the conformal basis. Instead, we have a factorization of 2D correlators into a sum over lower point correlators and an explicit conformal soft factor that only depends on the angles. Now, the angular dependence here is precisely the same as that of the soft factor in the momentum basis. And the explicit appearance of the energy of the kth particle in the soft factor on the momentum basis gets now mapped to a shift in the kth conformal dimension of the lower point correlators, which are summed over. Okay, so this is very nice because these two-dimensional correlators are a bit more exotic than the usual ones, but the universal factorization properties in momentum space gets now mapped into a universal conformal soft factorization in this conformal basis. Now, this result is perhaps both expected and surprising. It is expected because universal factorization properties of amplitudes should not be lost under a basis change. But on the other hand, this integral transform was over all the energies and in particular mixes the infrared with the ultraviolet. And so a priori, it was not clear how the energetically soft limit gets mapped to a momentum space, a conformal basis statement. But it's very nice that this universal property has a corresponding version in this conformal basis. Now, having accepted that translations get locally enhanced in asymptotically flat space, an immediate question is whether the Lorentz group doesn't also get locally enhanced. And this leads me to the discussion of the extended BMS group, which was originally conjectured, but has by now, I think, been solidified by various very nice results. So again, we start with a discussion of the boundary conditions. And now the extended BMS group contains a diffeomorphism psi, which rather than depending on a function, as in the BMS case, depends now on a vector field. And this vector field, y, is allowed to be singular on the two-sphere. Originally, such a vector field was disallowed. So all the singularities on the two-sphere were disallowed. And so the only thing that was left was the Lorentz group. But if you allow such singular vector fields, you get an enlarged symmetry group. And this corresponds to a diffeomorphism symmetry on the celestial sphere. The effect of this diffeomorphism psi on the metric is again a shift in the gravitational data, which for the ZZ component now takes the form of 3 covariant derivatives acting on this vector field now, and the factor of retarded time, or equivalently advanced time at the other boundary. What's now different to BMS is that also the leading metric gets shifted. So there's an inhomogeneous shift of the celestial sphere metric at leading order. And this will have important consequences when computing the soft charges associated to this symmetry. So physically, what this means is that the global rotations and boosts get now enhanced to angle-dependent superrotations, which are characterized by this vector field y. If this vector field is holomorphic, then this diffeomorphism psi gives rise to a Virasoro superrotation symmetry. While if y is an arbitrary vector field on the angles, it gives rise to a more general diffeomorphism symmetry. So in other words, the physical effect of this of adding these diffeomorphisms is that angular momentum is now conserved at every angle. Now, similarly to the leading case, to a BMS supertranslations, these new Virasoro and DFS2 superrotations are also related to other infrared gravitational effects, namely the spin memory effect, which is subleading to the gravitational displacement memory, and a subleading soft graviton. And unlike the leading cases, these effects were only found very recently. Now, let me zoom in a bit more on this relation between the water density of asymptotic symmetries and the subleading soft graviton theorem. So what was shown is that the subleading soft graviton theorem implies a water density for Virasoro symmetry when this vector field Y is holomorphic. Unfortunately, it appears that this relation is not bijective. And this has led people to suggest that perhaps we should extend the Virasoro symmetry group to all of diffeomorphism symmetry. So this means that the vector field Y should be allowed to be not only holomorphic, but any function on the celestial sphere. And what was found here was that the water identity for this symmetry group is actually equivalent with the subleading soft graviton theorem. However, the price to pay for this nice equivalence is that the phase space has to be enlarged. And the reason for that is that these diffeomorphisms change the metric on the celestial sphere at leading order. Now, what we'll find in a little bit is that when taking the perspective of this celestial CFD, or take the perspective of this conformal basis, we will find that particular vector fields Y are related between the Virasoro symmetry group and the DFS2 symmetry group. And in that sense, we can connect these two asymptotic symmetry groups and discuss in a bit more detail their differences and similarities. Now, in addition to the dimension 1 Goldstone mode, which gave rise to BMS symmetry, in this conformal basis, there are two more pure diffeomorphisms. There is one that arises when the dimension of the primary is taken to 0, and another one that is obtained when the shadow dimension of the shadow primary is taken to 2. Now, for this shadow primary of dimension 2, we have a diffeomorphism Xi2, which at the boundary gives rise to a shift in the physical state, which is given by this expression, where this vector field YZ is a holomorphic function 1 over Z minus W, which I gave here for a positive helicity graviton, as denoted by WW. Now, we will find that the conserved soft charge that is associated to this diffeomorphism symmetry is actually the two-dimensional stress tensor for 4D gravity. So this has weights 2, 0 for a positive helicity graviton. And the stress tensor is the generator of this Virasoro superrotation symmetry for holomorphic vector fields Y. On the other hand, for this dimension 0 Goldstone mode, we have a vector field that's non-meromorphic. And it turns out that the conserved charge with respect to this symmetry is actually the shadow transformation of this 2D stress tensor. So this has weights -1, 1, and it is the generator of a particular diffeomorphism symmetry, namely for this vector field, which for obvious reason we have denoted by a shadow superrotation symmetry. Now, the way I'm introducing this, it might seem rather natural that the conserved charges with respect to the symmetries should correspond to the stress tensor and its shadow. But from the asymptotic symmetry point of view, this is not at all obvious. In particular, since it was argued that the diffeomorphism group will give rise to radially divergent surface charges. And there's this issue about having to enlarge the phase space. So let me discuss these subtleties in a bit more detail and tell you how one obtains these soft charges being the stress tensor and its shadow. So this starts with the covariant phase space formalism and the computation of the Ayerwald symplectic structure. So this is done around a fixed background G for two variations, one of which will be taken to be either of these two Goldstone modes, H0 or H tilde2. So now the subtlety is the following. This diffeomorphism symmetry shifts the metric at leading order. So this is the celestial sphere metric that is changed at leading order. For the shadow dimension 2 primary, this shift is just a contact term. And previously in the literature, such contact terms have been dropped, which makes it look like that these two symmetry generators are actually on different footing. But what we'll do here instead is keep track carefully of all the contact terms. And this will show us that these two modes, which correspond to a Virasoro symmetry and diffus 2 symmetry, are actually on equal footing, at least as far as the computation of the soft charges is concerned. Okay, so this shift at leading order in the celestial sphere metric, what this does is it leads to a radially divergent symplectic structure. But fortunately, there exists a way to relomanize that, which was discussed in this paper. So what happens is that in the covariant phase space formalism, there is an ambiguity for adding boundary terms. And fortunately, the radial divergence that appears here is such a boundary term. And so we can subtract it. So after doing that, we obtain a renormalized symplectic structure, and we can furthermore integrate out this variation because everything will be linear in the fields. Now then there subsists a further residual ambiguity, but this corresponds to adding a finite boundary term, but this can be fixed by demanding consistency with the subleading soft theorem. So at the end of the day, what we find is the soft charge for Virasoro and diffus 2 superrotation symmetry. So this is for a general diffeomorphism symmetry, but specified to these two Goldstone modes that I've discussed. I should note that while this expression was rederived in harmonic gauge so that we can talk about these conformal primaries, it actually also agrees with previous results for diffus 2 symmetry in Bondi gauge. And it also agrees with the soft charge that was computed for Virasoro symmetry, where the contact terms have been dropped. So what happens here is that in this renormalization procedure, radially divergent contact terms and any other contact terms for this dimension 2 Goldstone mode get actually subtracted. And we are left with a function that is just holomorphic, 1 over z minus w to the 4. And this is all that remains in the soft charge for this dimension 2 shadow mode. On the other hand, for the dimension 0 primary, what happens is that the stuff that gets subtracted is some non-meromorphic function, while all that's left in the soft charge at the end of the day is given by a contact term. Now I can go back to the discussion of Virasoro versus diffus 2 superrotations. So what I've shown here is a superrotation symmetry for a particular vector field and the shadow superrotation symmetry for another particular vector field. And for this, we have found that these two symmetries are actually related by a shadow transform. Now, if we insist on having an equivalence between the subleading soft graviton theorem and the word identity of an asymptotic symmetry, what this suggests is that perhaps we should include the closure of Virasoro under these shadows within diffus 2. On the other hand, if from the celestial CFT perspective, there exists an argument that says, for example, that we should exclude the shadow stress tensor, then our results would say that the whole asymptotic symmetry group just reduces to the Virasoro subgroup. Now, let me come back to these mode operators that I introduced earlier. So what I can say now is that in the conformally soft limit, where this mode operator has the dimension delta taken to 0, or a mode operator defined for the shadow primary with dimension 2, these two mode operators are related by a shadow transform for opposite helicity. These mode operators are radially divergent, just like the symplectic structure, but after renormalizing them, they are what is given by the soft charge for superrotation symmetry, for the Virasoro symmetry, and for this particular shadow superrotation symmetry in diffus 2. And up to a numerical factor, the renormalized mode operators correspond precisely to the stress tensor and its shadow. So from the point of view of the celestial, putative celestial CFT, these two symmetries appear to be on equal footing via the shadow transform. Now, this brings me to my conclusion. So I have described to you a unified treatment of conformally soft Goldstone modes of spontaneously broken asymptotic symmetries with a view towards flat space holography. Massless particles here are described by conformal primary wave functions, that have dimension delta and spin j under the SL2Z Lorentz group, which is the global conformal group on the celestial sphere. Finite energy wave functions are mapped to wave functions with conformal dimension on the principal continuous series. And the energetically soft limit gets replaced by the conformally soft limit, where the conformal dimension takes certain integer values. And I've explained that these conformally soft modes do not augment the basis, but instead can be obtained from certain contour integrals of principal series wave functions. Now, I've also discussed a symplectically paired set of zero modes, namely the dimension 1 Goldstone mode and the conformally soft graviton, which is the celestial version of the soft graviton, and how it was subtle to find this conformally soft graviton in the conformal basis. I have also given you an example for a celestial analog of quantum field theory soft theorems, namely the conformal soft graviton theorem. But there exists by now many other instances of conformal soft theorems for Young-Mills, for example, where similar factorization properties were recovered in this two-dimensional conformal basis. Now, these two tables summarize the conformal primaries and their conformally soft limits, which give rise to asymptotic symmetries and soft charges. I have focused on spin 2, but there's also a story for spin 1. So it turns out that when spin 1 conformal primary has its conformal dimension taken to 1, it reduces to a large gauge transformation. This is again not a trivial gauge transformation, but a large gauge transformation, and corresponds to a U1 Kac-Moody symmetry. The corresponding soft charge is given by the soft photon and soft gluon current. And there exists an analogous story for the shadow primary, but this coincides with the primary of dimension 1. Then for the spin 2 graviton mode, we found that for the limit where delta goes to 1, we recover BMS symmetry generated by the BMS supertranslation current. And then for the subleading soft graviton case, we have found this dimension 0 primary and its dimension 2 shadow. And Virasoro superrotation symmetry is generated by the stress tensor, while the shadow stress tensor generates a diffeomorphism shadow superrotation symmetry. Now, this was about asymptotic symmetries and how they manifest themselves in a two-dimensional language in terms of this conformal basis. This is one question that has to be addressed for understanding flat space holography, so whether asymptotically flat space is holographic. But there are many more questions to be answered. And I think we will hear more along these lines in the course of this conference. So let me just finish by saying that flat space holography is very much a developing story. And with this, let me thank you for your attention.
So thank you very much, Andrea. Thank you. So just a reminder to everyone, if you'd like to ask questions, please put your hand up. In the meantime, let me read out a question from somebody who doesn't have a microphone. So this is a question from Igor Moll that everyone can see in the chat. And the question being asked is the following. So if you have a duality between a four-dimensional theory in Minkowski with a two-dimensional conformal field theory associated with a celestial sphere, it seems quite natural to think of generalizing the celestial sphere to a different compact Riemann surface with different genus. And really the questions are about that, you know, how would that work? What would the space-time picture would be? Would you still be able to have an asymptotically flat space-time? What would be the topology of the cuts of Scry? So can you comment on that?
Yeah, so while it's not my own work, going to higher dimensions, there have been works on extending each of those corners of this infrared triangle to higher dimensions. So of course, we can study scattering amplitudes in higher dimensions where we have soft limits. There exists work on looking at what are the asymptotic symmetries in higher dimension as well as memory effects. For the space-time part, of course, this depends on what boundary conditions you choose. And then depending on whether you go to higher dimensional odd or even dimension, there exist some subtleties that have to be dealt with. But in principle, there's no obstruction to extending this picture to high dimensions. And of course, one would hope this to be the case, because at the end of the day, if you think that the UV theory is a string theory, there should be an embedding in higher dimensions and also an embedding in string theory.
Yes, so just to say here, I think the question was not about going to higher dimensions. It was actually about taking a two-dimensional celestial sphere and replacing this with
replacing
a
that by a
compact
different
Riemann
dipole.
surface.
Okay. So yeah, well, the short question is, I have not studied that, or I have not thought about that.
My comment to that one would be, actually, it's hard to get something which is asymptotically locally flat if you're using surfaces which are not of positive curvature. And so if you go to, if you start thinking of torus, the torus or higher genus Riemann surfaces, they're of course 0 or negative curvature. And then you really struggle to make something asymptotically locally flat. So you might have to think about that. Okay, let me pass across to the first person who put his hand up, which was Andy Strominger.
Yeah, let me just comment on that last question. Sasha Zhiboidov and I wrote a paper maybe 4 years ago in which we talked about accelerating black holes that come out and puncture the celestial sphere and look like a sum over all operator insertions because their quantum states are correlated, and then sort of tie it into a torus. And that, so the symmetrics might be a context in which you might hope to get something that looks like a celestial torus. That's an idea we've tried to make more precise and haven't succeeded, but there might be something there. My question for Andrea is there any context, any sense in which there is or have you computed a central term in the OPE of the stress tensor and the shadow stress tensor?
That's a good question. I cannot answer that yet.
You're trying.
Yeah, we're trying to understand what the appearance of this shadow stress tensor means, and whether the algebra has to be enlarged to the full BMS algebra with diffeomorphism symmetry. Naively would say that you have either the primaries or the shadows, but you should not include them both. So we're trying to understand how this also fits with this conformally soft mode that we found by including the shadow. So we're trying to understand what is the minimum sets of ingredients that we really need, and whether all the rest is extra redundant information since it's related by a shadow transform. But yeah, that's a very interesting question.
Okay, thank you. Next question is from Tarek.
Hey, Andrea, nice talk.
Hi, Tarek.
Yeah, sorry if this is a basic question, but just to ask you about this pairing between operator and its shadow. So is what's going on there? So there are these things called supplementary series reps of the Lorentz group, and their inner product kind of looks like if you take an operator and its shadow and you integrate them. So am I supposed to think about it in that way in terms of the rep of the Lorentz group?
Well, this is a basic question, but that's why it's a difficult one. No, I have not studied these cross correlators yet. So they will for sure not be holomorphic like all the OPs with the stress tensor. But I don't know how to think of them yet in terms of more representation theory statements. But I will let you know as soon as we've computed them.
Thanks.
Thank you. There don't seem to be any more questions, so we thank Andrea again, and we will resume in about 10 minutes time for the final talk of the morning.
Hello.
Hey, how are you?
America, very good, and you?
Yeah, thanks. It looks like you're all set.
Can you see my slide? Can you see my pointer
Absolutely.
also?
I can see your slides. I can see your pointer. You look all set.
And they change.
It changes. Yeah, absolutely fine.
Perfect.
We'll just wait, a few more minutes as people have gone off to get their coffee or things and start.
Sure, sure.
Hi, Joao.
Hi, Jeff. How are you?
Good, thanks. Thanks for speaking.
Thank you very much for organizing this. I would guess it's a true challenge to organize such a big conference.
Surprisingly, I imagine I would probably be more stressed if everybody was in Cape Town to worry about getting on and off campus and stuff like that.
Yeah. But like this, something can go wrong, and then.
Yeah, that's true. We're learning a lot of tech, we're learning a lot about technology very, very fast.
But it means you will have to organize again some other year so that we can actually go to Cape Town.
Yeah, well, that's the plan. If such a thing as international travel exists again, then for sure.
Very good.
Yeah, the thinking was we'd run it online this year and then go to the back of the queue. Because next year it's supposed to be in Brazil, and the year after that is in Austria.
Right, so that's all planned already. It cannot be easily changed.
Yeah. We were there was lots of discussion about whether to N+1 it, but the logistics were a little bit too tricky. And this worked out nicely. I think it's nice to see just how big the community is.
Yeah, it's remarkable to see these numbers here. Well, below 300. What was the max so far? Do you keep track?
I think it was Okinawa. Hiroshi would know better, but
no. I mean, this week, what was the max
this
number
week?
of participants? Do you keep track?
2,200, maybe.
1,000.
2,200.
In one single talk.
Oh, in one single talk, the maximum we've had was about 600 and a bit, but then there's on the order of 200 or 300 people that are watching the live stream as well.
Right.
In Zoom, I think it's gone up to, I think I've seen up to about 600 and something. Yeah. We have space for 1,000. But on average, it's been about 350 or so. It peaks for some talks and then goes down again. There are currently 284 in the room right now.
Yeah, it's impressive.
Are you ready to start, Wei?
Sure, yes.
Okay. So we're very happy to have the last talk of the session on non-perturbative Mellin amplitudes. Go ahead, please.
Thank you very much. So let me thank the organizers for this privilege to speak at the biggest string conference ever. So this talk will be about work done in collaboration with Sasha Giboedo from CERN, Dean Carmi from EPFL, and my student João Silva, whose ability and perseverance was really essential to succeed in this project. Okay, so let me start with some just big picture motivation. So there are two parallel bootstrap programs that aim at understanding QFT or quantum gravity, either in anti-de Sitter space or in Minkowski spacetime. And the main observables on the left are boundary correlation functions, which are equivalent to Mellin amplitudes, as I will review briefly. While on the right, the main observables are scattering amplitudes. Okay, so Mellin amplitudes play a central role in establishing a concrete link between these two parallel bootstraps, because you can really take a Mellin amplitude and just take the flat space limit of ADS, sending the radius to infinity, and obtain scattering amplitudes. Okay, so that's, if you want, a generic motivation to study Mellin amplitudes. But our work has two more concrete motivations. So the first motivation is to constrain effective field theories in ADS. Okay? So a possible question is, does any seemingly healthy effective field theory in ADS can be UV completed to a consistent CFT? Okay. And so this question, you can answer yes or no. So if you are a hardcore string theorist, you're probably going to answer no. But if you are some more skeptical particle physicist, you may argue that if you get a healthy quantum field theory without gravitational anomalies, then you are able to couple it to gravity for sufficiently high Planck mass. Okay. So let me call these two different opinions the Garden conjecture and the Swampland conjecture. And it would be great to have some more general tool to address this debate. Okay, so the hope is that the bootstrap might play this role. And indeed, at the end of this talk and in our work, I will provide some rules that give a new handle into this question. Okay, so wait until the end to see what is the result. Okay, so the second motivation is very concrete. So the conformal bootstrap is very successful, but it's still expensive in the numerics sense. So it takes time to converge for many theories. So the question is, can we make the conformal bootstrap more efficient by setting it up in Mellin space? And there's good reasons to expect so, because Mellin amplitudes have been very successful, both at weak and at strong coupling in many different applications. So we would like to take them seriously and set up a non-perturbative bootstrap based on the Mellin amplitudes. Okay, so these are the main motivations. Okay, so my talk will have three main parts. So the first part will be try to really establish rigorously the existence of these Mellin amplitudes. The second part will be more pragmatic, to use this tool to obtain some CFT non-perturbative sum rules that then can constrain the CFT data. And the third part is actually applications of these sum rules in effective field theories in ADS, as I mentioned, and also the epsilon expansion. Okay, so before I start, let me just very quickly review the basics. So what is a Mellin amplitude? Well, they were introduced by Mach in 2009. So they are just a Mellin transform of a correlation function of scalar primary operators. So you see it's a function of the distances between the points, and you just transform the distances. So this gamma ij will be the Mellin variables. They are just dual to the distances. And And the Mellin amplitude is this function here. And okay, in the general case, there are some constraints. Not all variables are independent. In fact, there are as many integration variables as independent cross ratios. But in this talk, I will focus on the 4-point function of identical operators. So in this case, I can be very concrete. So the 4-point function of identical scalar operators in CFT can be written like that, where f and u and v are conformal invariant cross ratios. And you see here the Mellin representation is just a way of writing f of u and v as a double integral over u to some power, v to some power. Okay? The gamma 2 and gamma 4 are the integration variables. And just for later notice, so m is what we usually call Mellin amplitude, but sometimes also convenient to call this m hat, which includes these gamma functions. Okay? This is just notation. So why is this useful? Well, the first thing is that crossing symmetry becomes very simple. So crossing symmetry was this property of the correlation function position space. Okay, so this comes from permuting the external points. If you translate that to Mellin amplitudes, you see that it's just a permutation of the variables. If you think the Mellin amplitude is a function of 3 variables with 1 constraint, okay? Gamma 2, gamma 3, gamma 4. So this it's very analogous to what happens for scattering amplitudes in flat space if you think that these 3 variables are the Mendelssohn invariants ST and U. Okay? So that's just basic review of what I mean by Mellin amplitude. Okay, so let's start part 1. So we want to define the Mellin amplitude rigorously. So let's try, our goal would be to write a formula like this first one here at the top. Okay, where the integrals run parallel to the imaginary axis. Well, this is just some Mellin transform, and the inverse is the second line. So that could be the definition. Unfortunately, this integral does not exist. Okay, diverges in any conformal field theory, so this is not good enough to actually define non-perturbatively the Mellin amplitude. Okay, so now the basic idea, our basic strategy is very simple. We will just split this integral from 0 to infinity into 3 regions, here shown 1, 2, 3, which are actually related by crossing symmetry. So it's enough to do the integral in region 1, and then the other 2 are basically obtained by permuting the arguments. And the integral defines, we call that the k function. Okay, so it's an integral from 0 to 1. And now the advantage of this integral is that now it's really well defined, because as long as you take gamma 2 and gamma 4 bigger than delta, so this is the precise condition, this actually is completely analytic and convergent integral. So that defines k. And by doing that, now you can put the 3 pieces together and you immediately arrive at the following representation of the original correlator. So you have 3 terms because each region gives a contribution. And they all look similar, but the difference is in the integration contour. So each term is defined in a different region in this plane. So this plane, you should get used to it, is like the Mandelstam plane, if you want, for these Mellin variables. So we have 3 variables that have 1 constraint that sum to delta. So you can plot them in a 2D plane with the tilted axis like that. Okay. So each one of these integrals runs parallel to the imaginary axis over a point in the red region for the first, blue for the second, and green for the last. Okay? So this is an exact equation. And if it was not for different contours, we could just sum the integrands and define Mellin by a sum of 3 k's. Okay, so then it's clear what we should do. We should just analytically continue the k function beyond its definition from this integral. And then we can actually do it, deform the contours to the same contour and sum the integrands. So before doing that, let's just do an example of these k functions. It's already instructive. So let's take the 4-point function of a mean field theory. So this is just a disconnected part of the 4-point function. We can compute k, it's an elementary integral. And now you sum the 3 k's that define the Mellin amplitude, and you get exactly 0. Okay? So this is already something we learned. In this definition, the Mellin amplitude does not see the disconnected part. Okay, so the Mellin amplitude is the analog of the connected part of the scattering amplitude. Okay, so now let's address the problem of analytic continuation. So we have the function analytic in this quadrant. How to extend that to the rest? Actually, to the left, it's actually easy. We just have to use this operator product expansion, in particular the expansion at small u. It's actually the light cone expansion. And this converges inside the integration region. And we can show that by basically subtracting the leading singularities, we can extend the function to this region. Okay, so let me not give you all the details and just give you here the result. What you'll find, not surprisingly, is that you find poles at, let me show you here. So here you have powers of u, which are controlled by the twist tau of the exchanged operator in the operator product expansion of the external operators. Okay? So tau is the twist, so this is a very important variable in this talk, so keep it in mind. And since powers of u appear and you're integrating a Mellin transform like that, it's no surprise that you'll find poles when gamma12 is here. And of course, by crossing symmetry, you can also continue to this region. This function is symmetric under permutation gamma12, gamma14. And therefore, that's the analytic structure. So I would like to emphasize that since it's the twist that controls the position of the poles, we get accumulation points of poles. Okay, so it's well known, so from this work here from 2012, that in any CFT, there are double twist operators. So by that, what we mean is that there are operators that if you go to large spin, their twist approaches 2 delta plus 2n, okay? So this anomalous twist, if you want, goes to 0 at large spin. And that gives accumulation points of poles in the Mellin amplitude at 0, -1, so on and so forth. So actually, this is even richer because you don't have only double twist operators, you have triple twist, quadruple twist, so you have a nested accumulation points. Okay, so triple twist will give you accumulation points of accumulation points and so on and so forth. And in fact, it's an open question if the twist spectrum of a CFT in higher dimensions is discrete or continuous or dense if you want. Okay. In fact, it has recently been shown that in 2D irrational CFTs with C greater than 1, it's actually continuous or dense, the twist spectrum. Okay. So that shows you that the analytic structure of the Mellin amplitude is rather complex because it has all these essential singularities from accumulation points. Okay, so finally, let me just mention what happens in this corner here. So in this corner here, we don't have a full answer, but the natural guess is that you don't have anything else, that the only poles are the poles, the OPE poles that exist already in the other two quadrants. And we call this the maximum Mellin-Antistic conjecture. So what is the motivation for this? Well, one motivation comes from mathematics. So maybe you know this theorem. So there is a theorem in mathematics of analytic functions of two variables, that if a function is analytic in a tube, which is what we have here, so it's analytic for any value of the imaginary part and some domain of the real parts, then it's analytic in the convex hull of this tube. So if it was not for the accumulation points of poles, this theorem would actually imply precisely this maximum analytic conjecture. Okay? So because we have accumulation points of poles, you cannot apply this theorem directly. So the best we could do rigorously was to prove this conjecture in this small triangle when the minimal operator, when the external operator is the minimal twist. So this is already quite strong because this triangle includes the crossing symmetric point. So this is the point where these three variables, gamma 2, gamma, are equal and equal to delta over 3. So this is the natural point to bring all the contours together. And in particular, we arrive at this final straight contour formula where we can write the scattering, the correlator, as a Mellin representation, now with a straight contour. Everybody is in the same contour, And there are some extra terms that were produced by when we brought the three contours to the same contour, we crossed some poles, so that produces some extra contributions. But now this contour is on top of this crossing symmetric point here at the center of the Mandelstam plane. And in particular, if you apply this to the 4-point function of the sigma field in the Ising CFT, in the 3D Ising CFT, you find that actually the only subtractions that you need here are the disconnected part. So we proved that the 4-point function of the correlator in 3D Ising has indeed this straight contour Mellin representation. Okay, so that concludes the part one. So now in part two, we'll be a bit more pragmatic, and we'll really try to take this Mellin amplitude seriously and construct some rules that constrain CFT data. So the first ingredient that we need is Reggie-boundness. So this is quite well understood already in previous work, so I'll be very fast. So the idea here is that if you take the Reggie limit of a 4-point function in position space, so that's shown here in this picture, in terms of cross ratios, that corresponds to u going to 0 and v going to 1 after some small some analytic continuation, so shown here by this monodromy e to the 2 pi I in v. And one can show using the OPE that is still convergent in the S channel that this is actually bounded by the Euclidean 4-point function in this limit. And so this is a bounded one can derive just from CFT. And now if you use a Mellin representation of these correlators, you conclude that the Mellin amplitude cannot grow faster than linearly when one variable is fixed, so gamma 1, 4 is fixed, and gamma 1, 2 is going to infinity along the integration contour, okay, so along the imaginary axis. So unfortunately, this is not exactly sufficient for our purposes, so we extend this bound slightly. So what we will use is that actually this bound applies not just when you go along the imaginary axis, when you go to infinity along the imaginary axis, but when you go to infinity in any direction of the complex plane, except along the real axis. Okay. So that's the first property that we will use about Mellin amplitudes that will be crucial to write dispersion relations. The second property is Polyakov conditions. So what are these? So essentially, Polyakov conditions are the statement that in a generic CFT, one should not find integer powers in the OP, the operator product expansion, when you take operator 1 close to operator 2. But actually, Mellin spaces is much more transparent. So in Mellin space, at least naively, it looks quite obvious. So the Mellin amplitude M was defined as this M hat, which was the sum of 3 K functions, if you remember, divided by these gamma functions. But then, of course, gamma functions have poles and they are squared. So the Mellin amplitude should have double zeros at negative integers. Okay, so that's what I wrote here. 0 and the double zero is the second condition. So this would be what we call the naive Polyakov conditions. Why is it naive? Well, it's naive because we've just seen that these points are actually essential singularities of the Mellin amplitude. So they are accumulation points of poles. Okay, so recall that there are in any CFT double twist operators which have this twist, so whose anomalous dimension decay is at large spin. In fact, we know exactly how it decays at large spin. It decays at large spin with a power of spin controlled by the minimal twist of the theory after the identity operator. And therefore, the picture in the gamma 1, 2 plane is this. You have many, many poles, and each one corresponding to a different spin. And as spin increases, you accumulate at 0 or at -1. There is accumulation points at every negative integer. So this looks crazy. We're imposing a condition that a function has a double zero where it has an essential singularity. But if you remember string theory, it's not so crazy. So in the Veneziano amplitude, if we take the Regge limit, we do a similar analysis, right? When we send S to infinity, S equals infinity is an accumulation point of poles of the Lorentzian amplitude. But if we don't go along the real axis, if we go in any other direction, indeed we find that the function behaves as S to some power that depends on T, on the other variable. Okay, so this is exactly what we will find here. We will, if we approach this accumulation points from any direction different from the real axis, we will find a branch point behavior, a power law behavior controlled by the other variable. And this can be really computed. I won't show you the details, but we know everything because this is all controlled by the large spin behavior of the double twist operators, which we know, both the OP coefficients and the anomalous dimensions. So this is the result. So when you approach gamma 2 approach a negative integer, you find this power law behavior controlled by gamma 4 and this power law gamma 3 plus regular terms, which indeed have a double zero. And okay, then you can put it in a picture. So there is several regions. So the red region is where both exponents are positive, so the function goes to 0, and the green region is where both exponents are greater than 1, so the function goes to 0 faster than linearly. Okay, so the Polyakov conditions are, the non-perturbative Polyakov conditions are these conditions. Okay, so now we have everything we need to write a dispersion relation that then will lead to the sum rule. So dispersion relation is the standard trick. We just take a function and we write it as this identity using Cauchy theorem. It's equal to itself if you integrate around this pole. And now we just open the contour. Okay, so we open the contour and we pick all the other poles in the integrand. There are two important steps that we are using here. So one is that we are doing a subtracted dispersion relation. So we divide it by 2 powers of gamma 1, 2 if you want. So here gamma 1, 2 and gamma 1, 2 prime. So that the contour at infinity does not contribute. Recall that the Regge bound was linear, so we need to divide by 2 powers to make sure that integrand decays at infinity. The second thing we are using is that because we did subtractions, now we have extra poles which are not poles of M, which are these poles explicitly of the denominator. However, these are precisely chosen to be at the Polyakov conditions, gamma 1, 2 and gamma 1, 3 equals 0. Therefore, the residue will be M at those points, which vanishes by Polyakov condition. So with these two tricks, we can immediately write that by opening the contour, we get a representation of the Mellin amplitude just in terms of the residues of the Mellin amplitude, which we know. So the residues of the Mellin amplitude, we know that they are proportional to squares of OP coefficients and to a kinematical function, which is basically the Mach polynomial. Okay. So this is our main tool, this dispersion relation, and let me mention here related work. So in particular, in this work of Carmi and Caron, they also wrote a dispersion relation, which is the position space version of this formula. So, okay, so what can we do with it? Well, now that you have this dispersion relation, you can get some rules very easily. First, let's use crossing symmetry. So crossing symmetry between 1, 2 and 1, 3 is manifest. You see, the function is obviously symmetric, but between 1, 2 and 1, 4 is not. So this dispersion relation does not make crossing manifest in this channel. And so if you impose it, you'll get some rules, you'll get constraints. So in particular, let me choose this. It's just an example, but you get a simple and nice sum rule. Let's just choose gamma 1, 2 and gamma 1, 4 to be at this point, delta over 3. And then expanding this y. So clearly the first, since this should be symmetric, the first derivative must vanish. So if you do that, you get a sum rule of this type, where alpha is what we call a functional. It's completely explicit, okay? I wrote it here, doesn't matter the formula, but it's completely explicit function that depends on these kinematical functions Q, which are basically the Mach polynomials. Okay, but these are known in close, I mean, there are recursion relations to compute these functions to arbitrary order. Okay, so why is this sum rule interesting? Well, it's interesting because it has very remarkable properties. In particular, it seems to be the extremal functional for the maximization of the twist gap. So if you ask, how can I make a CFT with the biggest twist gap? What is the biggest twist gap compatible with the axioms of conformal field theory? This functional gives you the answer. Why is that? Well, the conjecture here is that we did not prove analytically, but we did extensive checks and various limits of this statement, that this functional is positive or non-negative for any twist above 2 delta. So it's plotted here. It actually has this form with many double zeros at 2 delta plus 2, 2 delta plus an even integer. And for the spin greater than 0, actually it has a single 0 at 2 delta. But they are all positive above 2 delta. If that is true, then it's clear that you cannot have a gap bigger than 2 delta. Because if you have gap bigger than 2 delta, you will have a sum of positive things being equal to 0. So the best you can do is put 2 delta, and then you have all the zeros, and that's just mean field theory. Okay. Okay, so finally, we did some checks. So this functional was obtained under some assumptions, which we did not fully prove. So we like to test it, and we like to test it non-perturbatively. So the best model to do that is to take the 3D Ising model, where we have lots of data. And in this model, this functional takes a very nice form. So because of this property that it's positive above 2 delta, most operators contribute here positively on the right, and only the leading Resi trajectory, so the operators below 2 delta, there is only one operator per spin, contribute negatively on this side. And we know a lot about all these operators. So for example, from this paper by David, you can pick up all the CFT data and you can compute this sum. So from the stress tensor and all the other spins. Okay, so the tail, you use some large spin asymptotics, you sum the tail. Okay, so on this side, we're pretty confident that we know that this is the number. On the right-hand side, it's harder because it's all the spectrum. We don't know all the spectrum, but we know a lot of operators. Okay, so David gives us tables of all OP coefficients and anomalous dimensions of a long list of operators. So we took that and we computed this sum, and we got that. Okay, so you can check that this matches up to 3% error. So it's perfectly compatible with the operators that are missing here, filling up the gap and satisfying this sum rule. So we take this as evidence. Okay, so we come to the final part of the talk, where I will now try to apply some of these sum rules to concrete models. So the first application is to effective field theories in ADS. So it's this idea that we want to constrain effective field theories in ADS, this garden versus swampland debate. So let me use the language of large N CFT, which is equivalent to the perturbative expansion in ADS. And it's important to keep in mind that there are two types of operators. So there's operators which are single trace, which correspond to single particles, so fields in the bulk. And those have OP coefficients with the external operators, which are order 1/n. And then there are double trace of the external operator, which have OP coefficients that are order 1, but have anomalous twist, which is order 1/n squared. Okay. So now if you apply our sum rule at large N, so to this weakly coupled effective field theory in ADS, or equivalent of this large N CFT, what do we find? We find, okay, this is the structure of the sum rule. Let me explain. So first term comes from light single trace operators. Okay, so if you have some exchange diagram, it will contribute here. The second term comes from the leading double trace trajectory. Okay, so recall that our functional has double zeros at every double twist. Therefore, since it has double zeros and the anomalous dimensions are of order 1/n squared, you get the contribution from the function to be of order 1/n to the fourth. Okay, so this is this error term here. The only exception is the leading twist trajectory, because, well, it was fast, but if you recall, it has single zeros at the leading twist when the twist is 2 delta. So that single zero you can expand and you get this contribution. So this is the derivative on that single zero and times the anomalous dimension, which is of order 1/n squared. And since this is already of order 1/n squared, the OP coefficients, you can just put the free ones, the mean field theory ones. And then the last term is everything else, so all the other heavy operators. So why is this sum rule interesting? Well, the remarkable fact is that the first two terms, let me call them H, the sum of the first two terms, so they are both of order 1/n squared, and they are just computable in effective field theory. Okay? It's just, you know, the couplings between the particle, between the different fields, and you know how that affects the anomalous dimensions of the leading two particle states. Okay? This is all effective field theory computable. The last term is not computable because it has to do with all the heavy, high energy stuff, but it's positive because the functional is positive and these are squares of OP coefficients. Therefore, you conclude that if you take some effective field theory, you compute H, and you find something positive, you can say this effective field theory is in the swampland. There is no way to save it. Okay, so this is, if you want a way, I think this is the most exciting thing about these sum rules, is that it really gives you a concrete handle in this debate if an effective field theory can be completed or not. Okay, and yeah, I should mention that there's similar ongoing work also based on position space methods by these authors. I've heard about that from some talks. Okay, so let's apply this in some theories and see what we get. So let's start from a simple theory, some scalar cubic theory in ADS. So let's say phi is the external dual to the external operator, and you have some other scalar field that can be exchanged. So you can compute these diagrams in effective field theory. And from these diagrams, you extract all the CFT data you need to compute H, and you get H equals 0. Okay, so this theory is perfectly consistent with the sum rule. It just gives 0, which means the UV does not contribute to this sum rule at leading order. So this is, I'm computing this to order lambda square, of course, which is the analog, lambda is the analog of 1/n in the previous slide. So now let's take another theory. Still a quantum field theory. Okay, so far I'm not putting gravity. So this theory is another scalar theory, but now with a quartic interaction. But let's take this derivatively coupled. So actually, in this theory, if you compute H, which is again perfectly computable, you find that H is proportional to lambda. So lambda is already times a positive minus lambda times a positive number. Okay. So therefore, since H has to be cannot be positive, you conclude that lambda has to be positive. Okay. But it's true that we exclude some effective field theory, but there's nothing that particle physicists don't know already. So this is well known from this paper. So yeah, I wouldn't consider this a new swampland constraint, right? This is it's something you can derive in flat space just from some dispersion relation trick. Finally, let me consider the coupling to graviton. So let's take the scalar just minimally coupled to graviton. So then you have to sum up these three graviton exchange diagrams. And again, this is, we know how to do it. And we can compute H, and we find H to be negative. Okay. So in this case, again, we cannot exclude the theory. And because we actually expect the UV to contribute something in this theory. because we know that at 3-level graviton exchange grows with energy faster than what we imposed in the Regge limit. Therefore, we expect indeed something coming from the UV. So everything is consistent. So I would say that the summary is that at the moment, these sum rules and the bootstrap is still not able to put any effective field theory in the swampland. But I think this definitely deserves further study, and maybe tomorrow someone will find the right functional in the right theory to actually exclude one seemingly healthy effective field theory. Okay, so
about 3 or 4 minutes left.
Very good, very good. I'm really finishing. So last application, epsilon expansion. So now this is a purely field theory application, just the Wilson-Fisher fixed point. So this is just some conventions for the anomalous dimensions of the field phi and the double twist operators. And here we again start from the same dispersion relation that we had before for the 4-point function of phi. But we, instead of imposing crossing, we impose another Polakov condition. Okay, we found this to be more convenient. So if you impose the next Polakov condition at gamma 1 equals -1, you get an equation for any value of gamma 1,4, or actually for gamma 1,4 in a given range. Okay, but it's still a free parameter. So this is actually an infinite number of equations, which if you work through them carefully, I don't have time to explain, you can show that this equation fixes all anomalous dimensions to leading order. Okay, so the anomalous dimensions, so all phi square if you want, and the leading twist trajectory. And in fact, well, but this is the usual story. If you also impose that the stress tensor does not have an anomalous dimension, then that will also fix the anomalous dimension of phi itself. So this is work in progress, but we clearly see that by imposing other Polakov conditions and taking these equations to higher orders in epsilon, we can systematically get access to more and more CFT data in the epsilon expansion. Okay? So this is very, very, very similar in structure to this Mellin Polakov bootstrap from these authors here. But the advantage now is that really we think we have systematic equations that we can go to any order in epsilon that make this problem, this approach really systematic. Okay, so let me conclude with a list of future work. There's a lot of work to do. So first point, there's like prove our 2 main assumptions, the maximum analyticity and the extended Regge bound. These are the 2 main assumptions that go into our work. Then, of course, there are extensions to different operators, spinning, higher point from bound. I mean, lots of interesting problems that also would benefit from a Mellin space approach. And then these last two points here in the middle are directly related to the numerical bootstrap. So what do we need? We need to actually construct a basis of efficient functionals. So what I explained to you was a bit on a ad hoc way of constructing functionals, but so we would like to have a basis, systematic, and then implement it numerically. Okay, so this is something that basically can be done in the near future, and it would be good to see how efficient it becomes. And then this I already mentioned. I think it's a complete open question if we can find another sum rule that can actually place a seemingly healthy effective field theory in the swampland. It's an open question. And let me end with an invitation for the next talk. So it's more related to our real world. So are Mellin amplitudes useful in the sitter? So please continue with Charlotte's talk after me. Thank you very much.
Okay, thank you. So moving to questions. The first question I see is from Abhijit.
Hi.
Hi, Abhijit.
Hi. So if you consider phi to the 4 theory in the bulk, then the sum rule seems to put a constraint on the sign of the coupling. That would
del phi to the 4, yes.
Not del phi to the 4. Just let's say phi to the.
Just phi to the 4 it doesn't. So actually at leading order it just vanished because. So phi to the 4 only gives anomalous. So first of all, there are no single trace exchanges, only double trace.
Mhm.
And it only gives anomalous dimensions to the spin 0 double trace. And if you remember, the spin 0 functional has double zeros everywhere. So it will immediately give you an order lambda square contribution. There is no order lambda contribution. That vanishes identically.
I see. But if you consider, let's say, higher derivative 4-point couplings, then you would get a system of inequalities, presumably, right?
You mean if I put even more derivatives than these 4 derivatives?
Yeah.
Yes.
So those would be unfamiliar constraints.
Well, I think it's a matter of how you choose the basis of effective field theory couplings, right?
Well, you can organize them by derivatives to begin with, let's say.
Sorry?
You can organize them by derivative, number of derivatives.
Right. If you do that in flat space, then the derivatives will correspond to powers of S in the scattering amplitude. And so you can really split. So must be positive is the coefficient of S squared, right? In the scattering amplitude in flat space. So here, what really this is measuring is the anomalous dimension. So in this case, it's the spin 2 double twist operator that gets an anomalous dimension that has to be negative, cannot be positive.
Mm-hmm.
But if you just write derivatives at finite radius of ADS, all these things will in principle contribute some bit for this anomalous dimension. And so that's why you get a mixture. But that's more of a difficulty of splitting the basis in ADS when you have finite radius. The power of derivative is not really sufficient to split this basis.
Thank you.
Okay, the next question is from Ivo Sachs.
Very impressive talk, thanks. So my question is, you said that these sum rules at large n, they are related to perturbation theory in ADS. So the first question is there any way to track renormalization in the bulk and renormalizability? And the second question would be, if there were to be a cutoff, is there any way to see this cutoff on the sum rule side or on the Mellin side?
Thank you. Yeah, I think that's a good question. So I think the fact that you need a cutoff in the effective field theory is related to the fact that if these heavy operators contribute or not in perturbation theory. So let me try to explain. So if in perturbation theory, your amplitude, let's think in flat space, in Mellin space is very similar. In perturbation theory, your amplitude grows with energy, then you know that you need a cutoff, right? You will violate unitarity at some point in perturbation theory. So what does it mean for this sum rule? It means that if it grows in energy, it means the anomalous dimensions also grow with the twist, which makes this part of this heavy part actually contribute non-zero. So basically, we can distinguish a theory that needs a UV cutoff by the fact if these heavy operators contribute positively or not.
Mm-hmm.
Did I answer your question?
Yes, about the cutoff, I think. I mean, the cutoff dependence is probably not manifest. But, you could see that there's one, but how predictions depend on the cutoff. Perhaps that might be hard to extract.
Yes. That you can get some scalings. That sometimes you can get that you can show that this contribution has to enter. For example, in the case of del phi to the 4th, that you see that you get a contribution of order lambda from these two terms. Then you need also contribution of order lambda from heavy. That you can show, but we could not compute the number. We just can show that it's of order lambda. That we can.
Thank you.
Thank you.
Okay, I see no more questions from people with their hands up, although a number of kind of discussions in the chat. So I suggest we just thank the speaker again. And this will be the end of this session. We'll come back at 5 o'clock with Igor chairing the next session. Thank you.
Thank you.
Hi, Igor, are you there?
Hello, yeah, I'm here. How are you?
Hi, Igor. Okay, so I've made you co-host as well as Charlotte.
Great, I'm here.
Oh, great, excellent. Charlotte, would you like to just check that your slides work?
Sure, let me also start the video. Remember how.
Hello.
Hi, Igor.
Hi, Igor. So, can you see my slides?
Yep.
Can you also see my cursor?
Yes.
Perfect. Okay. There's no other stuff like from my laptop that you can see, or
No.
I don't know. I mean, this happened to me once in a conference talk. There was something like lingering on the bottom right.
No,
So I'm paranoid about this.
No. Okay. So we'll start in 10 minutes.
Yeah, that's perfect.
So Charlotte, I'll give you 5 minute and 1 minute warnings. So
Okay, that's good.
Just verbally.
Yep.
I apologize in advance for interrupting, but this is my job.
No, please do your job. I'm not going to stop you doing that. By the way, you can't hear any like noise pollution from my side, right? Because I live on a busy street, and right now there's a big van outside doing some unloading.
Yeah, I haven't heard anything. Where are you now? In Brussels? Or?
No, I'm in on Nassau Street. I'm in Princeton.
Oh, you are on Nassau. Okay.
I think the pancake place is getting daily delivery.
But Panera is closed, right? That should reduce the noise.
Yeah. So Panera is closed, but all the other stuff is open, like PJs and yeah, this outside seating.
PJs is open?
Yeah, PJs is open. It's right below me.
Oh, wow.
Yeah, I mean, the tables are pretty full. So.
Must be hard to work with all this pancake smells going on.
yeah. In the downside, there's a lot of smell of fat, and there's also this burger place which is very smelly as well.
Is Small World open?
Small World, yes, it is open. You even have the
or sit down.
Sorry?
Or sit down or just takeaway?
It's takeaway. As far as I can
tell,
you
can sit. You can probably sit outdoors now.
Yeah.
Yeah, they blocked off Witherspoon Street, so there are tables outside. It's now one way, so there are tables. And, but I don't think you can eat indoors anywhere yet. At least I wouldn't try it. Yeah, it's been a long lockdown.
Yeah.
How long has it been for you guys in Princeton?
Well, I think from March 21st was the New Jersey lockdown order.
Yeah.
But here the epidemic seems way down. I mean, in LA, it's in a way the worst. In California, because they've been on lockdown from mid-March, and now for real, things are bad there, I think.
At least in Princeton recently, things have got better because like the shops and the restaurants have started to open with outdoor seating.
Yeah.
So it's a little bit less isolated.
The epidemic in Princeton was never particularly noticeable. I mean, the cases was very limited. I think.
But what will happen next year is teaching completely online in Princeton.
No, we don't know. We actually don't know yet. I think they're still reassessing. I mean, in view of this new wave down south, I think it's.
You can wear one of these if you have to lecture in person. You can wear one of these, like steampunk style plague suits, where you look like a crow.
Yeah, I lectured online all through the second half of the semester, and that was fine actually.
Shall we start?
I'm ready. Turn on the video.
Okay, so welcome back to the second session for the day. Our session chair is Igor Klebanov from Princeton, and Igor will introduce the next speaker.
Okay, thank you very much, Jeff, and it's an honor to be a session chair in this first ever global online strings conference. I'm personally grateful to the organizers in Cape Town for running this event. I think we all need some engagement and boost. So the first speaker will be Charlotte Slight from IIS Princeton and ULB Brussels, who will tell us about Mellin Barnes' approach to scattering in de Sitter space.
Okay.
Thank you.
Thank you, Igor, for the introduction, and to the organizers for creating this fantastic virtual stringy experience, and of course for this opportunity to speak. So obviously I'm going to be speaking about scattering in de Sitter space. These other words in my title essentially say that we've been developing some new techniques to study them. And I'll be speaking, okay, how does it go? I'll be mostly speaking about work in collaboration with Massimo Torrone, who's also here on Zoom under this picture here. So the imprints of these scattering processes that take place in a de Sitter spacetime are encoded in correlation functions on its boundaries at infinity, which, as I recall here on the slide, are spatial slices in the very far past and in the very far future. So there are various reasons why studying these types of observables might be interesting. So for instance, this provides us with an example of holography where time is emergent. So instead of only space, like in the plain vanilla ADS-CFT setting. So this is like a step away from the relative security of the ADS-CFT correspondence in a direction where we might potentially learn something fundamentally new about holography itself, so the emergence of time. While at the same time, this setup retains some familiar features that we might look to for reassurance or try to take advantage of. And one of these that we will see in this talk is the fact that these boundaries at infinity are conformal. So the corresponding observables are constrained by conformal symmetry, just like in ADS-CFT. And let me stress that this statement is purely about kinematics and doesn't rely on the existence of a dual CFT description. So in this talk, I'm going to focus on scattering processes where all of the external legs lie on this boundary at future infinity. And the corresponding observables are of particular interest from the perspective of inflationary cosmology, which, as we know, postulates that the very early universe had this period of by the de Sitter spacetime. And one of the main predictions is that spatial correlations at the end of inflation, so like these guys are here, so say the scalar or the tensor fluctuations, the prediction is that as time evolves forward, these correlations give rise to correlations, for instance, in the CMB, in the distribution of galaxies. And so this would make inflation the highest energy observable natural process, where in particular the energy of the Hubble scale during inflation could be as high as 10 to the 14 GeV. So inflation therefore presents us with this really incredible opportunity to try to probe the laws of physics at these scales, which so far remain somewhat elusive. And the task that we have ahead is to classify the effects of new degrees of freedom that might become observable at these scales. So to classify the imprints of possible processes that can take place, for instance, here in these question marks. And this is in order to compare with future observations of these guys. So what I've just outlined is what is known as the Cosmological Collider Physics program, and it's been pioneered by numerous groups, some of which I put here on the top of the slide, and sorry for any omission. And this is essentially where we view this inflationary expansion as this insane high energy particle collider. So in order to reach the goals of this program, we need to develop systematic techniques, not only to blindly evaluate these boundary correlation functions, but also to try to gain a better understanding of their structure. And although, of course, we don't have an understanding which rivals that which we have for scattering amplitudes in flat space, in recent years there has been significant progress in this direction, which nonetheless has drawn inspiration from the successes and the strengths of the scattering amplitudes program. But key steps have been taken by these groups here at the bottom of the slide. So in a similar way, it's worth noting that many of the goals of the cosmological collider physics program are in some way shared by those in the parallel program in anti-de Sitter space. So in ADS, we have a pretty good understanding of the structure of boundary correlators, not only at tree level, but also beyond. Where in ADS, we have a bit of an edge compared to flat space because we can make use of the ADS CFT correspondence, where in particular, all of our questions and confusions about observables and asymptotically anti-de Sitter space can be translated to sharp questions about the consistency of correlation functions in conformal field theory, which are defined in terms of conformal symmetry, unitarity, and a consistent operator product expansion. So a natural question that one might ask at this point is whether any of the techniques which led to this type of progress in ADS can be adapted to de Sitter. And this question is not so crazy because at the end of the day, many of these techniques were developed in Euclidean ADS, which is the same as the isometry group in de Sitter. So you don't have to fall over with shock if it does turn out that there are things that do carry over. But despite these similarities, there are also major differences. And one of these, of course, is that the de Sitter background is time dependent. So if you want to compute fixed time correlators like those that we're interested in on the boundary at future infinity, the standard framework that you have to use is a so-called Schwinger-Keldysh or in formalism. So this is where you have to be careful with the bulk time integral, and you first have to make sure that you integrate in a time-ordered fashion along the so-called plus branch of the in contour. And then once you've done that, you don't have to forget to integrate back in an anti-time ordered fashion along the so-called minus branch of the in contour. So these type of differences with respect to Euclidean ADS, they make at least a direct application of many of these techniques far from straightforward, at least in the current way that they are formulated. So one of the main objectives of the work that I'm going to tell you about was to see if there's some way to level the playing field between boundary correlators in these two spacetimes. And to this end, we found it rather useful to adopt a type of Mellin-Barnes representation of boundary correlators in momentum space. So Mellin-Barnes integrals, we know, are contour integrals which involve products and ratios of gamma functions. And the integration contour is usually taken to run parallel to the imaginary axis. So for some boundary correlator describing a scattering process in a bulk spacetime, this Mellin-Barnes representation that we define, in this representation, each external leg in this scattering process with some boundary momentum Ki is described by what I call a single external Mellin variable Si, where the boundary momentum Ki enters this Mellin representation with an exponent that is fixed by the corresponding external Mellin variable, as well as the scaling dimension of the corresponding operator on the boundary. And this is accompanied by two infinite families of poles, which are the poles in the Mellin-Barnes representation of the corresponding external propagator. Function. So I plotted these poles here, right? They're integer space and head off to minus infinity. So of course they're encoded in some gamma functions. And the location of these poles depends on the mass of the external particle, which enters in the usual way through the scaling dimension delta I. So these features that I've just outlined, they actually become rather suggestive when you note that just like how translation invariance enforces momentum conservation, and the dilatation warded entities of our conformal correlation functions, they imply a similar constraint on the external Mellin variables. So they have to sum up to a constant, and I will give some examples of this constant in a moment. Moreover, just like how the momentum conserving delta function arises from an integral over position x over the boundary, the delta function that enforces this constraint on the external Mellin variables can be expressed in a similar way now as an integral over the bulk radial coordinate, which in Poincare coordinates, which we use throughout in our computations, is usually called z. So these parallels between momentum space and this Mellin-Barnes representation, they continue, and you will see more of them as the talk progresses. And they all make it kind of tempting to suggest that this Mellin-Barnes representation could be some kind of natural habitat for conformal correlation functions in momentum space. But this we haven't substantiated beyond just noting these nice parallels between these two pictures. So the simplest type of boundary correlator is that which corresponds to a 3-point contact diagram. So these only have external legs, and there are 3 of them. So in the Mellin bands representation, there are 3 external Mellin variables, 1 associated to each external leg. Translation invariance enforces momentum conservation, and the dilatation ward identities require that these external Mellin variables sum up to this constant here, which you see depends on the boundary dimension d and the spins j of the fields that enter in this cubic vertex. If you also have an internal leg, like in a 4-point exchange, each internal leg in the scattering process in this Mellin representation is described by a pair of internal Mellin variables u and u bar, where the corresponding internal momentum enters the Mellin representation in the way that you see here on the slide. And just like how the internal momentum is related to the external momentum through momentum conservation at a cubic vertex, these internal Mellin variables u and u bar are related to the external Mellin variables through the constraint that we saw on the previous slide on Mellin variables that are connected through a cubic vertex. So what we found is that by adopting such a type of Mellin bands representation for boundary correlators in these 2 spacetimes, and we found that this places their computation on a more equal footing. And a key observation is that propagators in this framework take a universal form, and they're constructed out of what are essentially 3 basic building blocks. So focusing first on the propagator in Euclidean ADS, the first building block, the green one, is the corresponding harmonic function. So it solves the source-free equation of motion. And this means that in the Mellin representation of this harmonic function, the poles in the internal Mellin variables u and u bar, they encode the contribution from the physical exchange single particle state. So where the boundary condition is enforced by this middle building block, the yellow one, which is a linear combination of these functions omega d and omega n, whose role is to implement respectively the Dirichlet and Neumann boundary conditions, where the most general boundary condition is a linear combination of the 2. So these functions, omega d and omega n, they're entire functions of these internal Mellin variables, so they don't contribute any pole to this Mellin representation. And you see here on the slide that they have a simple explicit form. So they have a factorized dependence on these internal Mellin variables, which is given by a simple product of sine functions. And as you will see in a few slides, essentially what happens is that the zeros of these sine functions overlap with the poles of the harmonic function that violate the boundary condition that you want to implement out of Dirichlet and Neumann. So these functions, omega d and omega n, they serve as projectors onto these boundary conditions. The final building block is this cosecant factor, and as is written, its role is to encode the contact terms in the exchange process. So the combination of the green and the yellow building blocks so far just satisfy the source-free equation of motion with some boundary conditions. And this cosecant factor ensures that the propagator satisfies the equation of motion with a source. So if you put the internal leg on shell, so if you take the cut or the discontinuity with respect to the internal momentum, this cosecant factor you see gets cancelled, and this is the on-shell form of the propagator. Moving over to de Sitter, formalism to each field, there is associated 4 propagators, since these 2 points can each either sit on the plus or minus branch of the in contour. And each of these propagators take the same form as their counterpart in undilated space. So they're built from analogous building blocks which have the same role as their ADS counterparts. So these projectors omega d and omega n, they have exactly the same form. And their interpretation in this context is that they're projecting onto the delta plus and delta minus late time behaviors of the exchange field, where the precise linear combination of the 2 is fixed by our choice of vacuum at early times. And for the vacuum that we all know and love, the Bunch-Davies vacuum, this corresponds to this choice of the coefficients alpha and beta here. So the crucial bridge between propagators in these 2 spacetimes is that at the level of this Mellin bands representation, the harmonic function in de Sitter space is given by its counterpart in Euclidean ADS multiplied by 2 very simple phases that are associated to each point in the harmonic function. So you see that the sign of these phases depends on which branch of the in contour that this harmonic function in these 2 points are sitting on. And you can establish this relation by simply Wick rotating from ADS to DS. So you can take your harmonic function in Euclidean ADS in Poincare coordinates, you establish its Mellin bands representation, and then you wick rotate to the Poincare coordinates in de Sitter, where the direction of rotation, so clockwise or anti-clockwise, dictates which branch of the in contour that you land on, so plus or minus. If you take the boundary limit, you get bulk boundary propagators. And in the same way for a given boundary behavior, which I call delta, which can either be delta plus or delta minus, a bulk boundary propagator in de Sitter is given by its counterpart in Euclidean ADS multiplied by the same type of simple phase, where again, the sign of this phase depends on which branch of the in contour that this point in the bulk is sitting on. So these observations are significant because they tell us that the differences between boundary correlators in these two spacetimes amounts to a simple collection of phases. So this framework really provides a setting in which you can try to extend in quite a concrete way, as we will see, existing techniques and results from ADS to DS. You just have to reformulate them in the language of this Mellin bands representation. This framework also gives us a new systematic understanding of boundary correlators. So as we will see, constructing boundary correlators in this framework amounts to combining these basic building blocks together in a consistent fashion. So for the rest of this talk, I'm going to explain how we put these ideas into practice whilst still keeping our feet firmly tethered to the ground, so sticking to tree-level processes throughout. And we'll start off with the three-point contact diagrams, which are the basic building blocks from which we can construct more complicated observables. And we'll see how this Mellin formalism allows us to immediately express a contact diagram in de Sitter in terms of its counterpart in anti-de Sitter space, for which expressions are available for any triplet of particles, so of any mass, spin, and cubic coupling that connects them. We'll then move on to 4-point exchanges, and we'll see how, given the knowledge of the constituent 3-point contact diagram, and the Mellin formalism allows us to quite straightforwardly implement the basic consistency criteria that determine the corresponding tree-level exchange. And at the end of the talk, given these results, I'll explain a little bit what we can uncover about exchanges and interactions in de Sitter using this framework. So as I just said, we can construct a contact diagram. We can obtain a contact diagram in de Sitter starting from its counterpart in anti-de Sitter space. And the way you proceed is you take the Mellin bands representation of your ADS contact diagram, which you can establish in your favorite way. And what we did is we Fourier transformed existing known expressions in ADS. And then once you've done that, you simply multiply each leg by the phase which converts it to a bulk boundary propagator in de Sitter on a particular branch of the in contour. So this gives the contribution from that branch to the de Sitter contact diagram. The overall phase that you get when you apply this procedure is a constant because the sum of the external Mellin variables that appear in this phase is a constant by virtue of the dilatation Ward density that we saw earlier on. So this constant phase depends on the boundary dimension d and the scaling dimensions of the fields and their spin. The final step to get the full de Sitter contact diagram, you simply have to add the two contributions together from the plus and minus branches of the in contour, where these constant phases, which have opposite signs, they combine to give a sinusoidal factor multiplying the corresponding contact diagram in anti-de Sitter space. So this sinusoidal factor is putting the interface between the contributing branches of the in contour. So what can happen, for instance, is that the de Sitter contact diagram can be vanishing, even if the ADS contact diagram is not, due to a presence of a zero of this sign function for some values of the boundary dimension d, the scaling dimensions, and the spin. Another thing that can happen is that the ADS contact diagram can have a singularity, which is subsequently cancelled by a zero of this sign function. So a famous example where this happens is the conformally coupled scalar in ADS4. So the ADS contact diagram as a singularity. In this case, this singularity is cancelled by a sign function, rendering the de Sitter contact diagram finite. So now that we've covered contact diagrams, we can move on to more interesting observables, such as exchanges. And as I said, given the knowledge of these constituent 3-point contact diagrams, the Mellin formalism allows us to straightforwardly implement the basic consistency criteria to construct the corresponding exchange. And this works in the same way for both ADS and DS. So let me first explain how this works in ADS, for which we maybe have a little bit more prior intuition. So as we saw a few slides ago, in this Mellin formalism, an exchange can be reconstructed from its on-shell piece by multiplying with this cosecant factor that encodes the contact terms. So this has quite significant consequences when it comes to constructing boundary correlators in this framework, because it means that you can focus on the on-shell piece, which is a much simpler object to deal with and to construct. So in the following, we can just focus on the on-shell exchange, and we're done. And the on-shell exchange is determined by a combination of factorization, so like in flat space due to locality, as well as conformal symmetry and any boundary conditions that you want your fields to satisfy. So we've seen that boundary conditions are quite straightforward to implement in this Mellin formalism. So it amounts to a projection operation in these internal Mellin variables, u and u bar. So let's first focus on the requirement of factorization and conformal symmetry. So for factorization, you can just take the constituent 3-point contact diagrams and multiply them together. And when you do that, there's a unique object that you can form, which is consistent with conformal symmetry, and it's this guy here on the slide. So where the internal leg from one of the 3-point factors is subject to the delta plus boundary condition, and the other is subject to the delta minus boundary condition. So in conformal field theory, this object is often called a conformal partial wave. It has some nice properties. In particular, it's a single-valued eigenfunction of the conformal Casimirs. And in this setting, this conformal partial wave is normalized so that it's consistent with factorization in anti-de Sitter space. So this object is consistent with factorization and conformal symmetry. It describes the on-shell exchange of a particle in anti-de Sitter space with a boundary condition that is fixed by the definition of the conformal partial wave itself. So it's some linear combination of delta plus and delta minus. So to access more general boundary conditions, the key is that this conformal partial wave is the boundary dual object of the harmonic function in the bulk, which we were using to construct our propagators earlier on. So the quadratic Casimir equation is equivalent to the source-free equation of motion satisfied by this harmonic function. And this duality is made manifest by the so-called split representation of harmonic functions. So where they factorize into a product of two bulk boundary propagators, one subject to the delta plus boundary condition and the other subject to the delta minus boundary condition. So you can go from one picture to the other by just attaching and removing the external legs. So this relation means that we can implement a given boundary condition by multiplying the conformal partial wave with the appropriate linear combination of our projectors, omega d and omega n, that implement that boundary condition at the level of the on-shell propagator, like we saw at the beginning of this talk. So this is the final form for the on-shell exchange, which we fixed by a combination of factorization, conformal symmetry, and boundary conditions. And we saw these conditions are quite straightforward to implement in this Mellin formalism. It just amounted to combining these basic building blocks together in a consistent fashion. So notice that in obtaining this expression, we didn't have to evaluate any complicated bulk integral because we essentially bootstrapped it from the knowledge of the constituent 3-point contact diagrams. And of course, the final step, so to reconstruct the full exchange from its on-shell piece, is to multiply by this cosecant factor that encodes the contact terms. So as you will see, the poles in U and U bar that are introduced by this cosecant factor, they generate the effective field theory part of the on-shell piece. So given the similarities between boundary correlators in ADS and DS that are made manifest by this framework, each of the steps that we've just taken to determine this exchange in anti-de Sitter space can be carried over to de Sitter. So within in formalism, we know that the exchange in de Sitter decomposes into 4 pieces. And each of these contributions is on-shell is individually fixed by the requirement of factorization, conformal symmetry, and boundary conditions. So we can determine each of them in precisely the same way like we did in anti-de Sitter space. So for a given contribution, for factorization, you again take the constituent 3-point contact diagrams from the appropriate branches of the in contour. And the unique object that you can form that is consistent with conformal symmetry is again the conformal partial wave. And the conformal partial wave that you get is proportional to that which we saw in the ADS case, because in particular we saw earlier on that 3-point contact diagrams in ADS and DS differ by this constant phase. So in this setting, the conformal partial wave is normalized so that it's consistent with factorization in de Sitter as opposed to in ADS. And at this level, you can effortlessly pass between these two spacetimes. For instance, starting with the conformal partial wave in anti-de Sitter space, and multiplying each leg by the phase that implements like the wick rotation to the appropriate branch of the in contour in de Sitter. So from this point, we can just essentially continue like we did in anti-de Sitter space. So to impose a given late time behavior on our exchanged field, you simply multiply the conformal partial wave by the appropriate linear combination of projectors omega d and omega n that implement that boundary condition at the level of the corresponding propagator. So just like in ADS, using factorization, conformal symmetry, and boundary conditions, we fix the on-shell exchange in de Sitter. And the final step, as before, to reconstruct the full exchange from its on-shell piece, you have to multiply by this cosecant factor that encodes the contact terms. So given this expression, let's explore a little bit what we can uncover about exchanges in de Sitter using this framework. And in the following for concreteness, I will focus on correlators in the Bunch-Davis vacuum, which we recall corresponds to these concrete choices for the coefficients alpha and beta. So the signal that a particle exchange has taken place, so the signal that would distinguish it from a local quartic contact interaction, and this is particularly sharp in the limit where the exchange momentum Ki is soft, which in position space on the boundary corresponds to taking these two pairs of points to be far apart. So the behavior of your 4-point correlator in this limit is a good diagnostic of whether or not a particle has been exchanged between these two pairs of points. So this limit of exchanges in de Sitter and anti-de Sitter space has been explored in numerous works. Our analysis is most similar in spirit to these works here on the bottom of the slide by Kanemed and the collaborators. So there they also used conformal symmetry and general consistency to classify such signatures at tree level in the case of external conformally coupled and massless scalars in D=3. And using the results from Mellin formalism, we could generalize their results to a generic collection of particles and general boundary dimensions D. So it turns out that this Mellin formalism is quite a useful tool to explore soft limits in any of the momenta. So where the expansion of your boundary correlator in these limits is generated by the residues of poles in the corresponding Mellin variable. So for the soft limit of the internal momentum, these are the poles in the internal Mellin variables U and U bar. So for the on-shell exchange, which we know it encodes the physical exchange single particle state, the only source of poles in U and U bar comes from the constituent 3-point contact diagrams, which are recalled here on the bottom left. These are precisely the same poles that we saw earlier on in the talk. And they're in the same location for both U and U bar. They're these two infinite families that are integer spaced and head off to minus infinity. And their location depends on the mass of the exchange particle. So this is somewhat analogous to exchanges in flat space, where the contribution from the physical exchanged single particle state is generated by the residue of a simple pole whose location depends on the mass of the exchanged particle. So the residues of these poles generate the expansion of the on-shell exchange in this soft limit. And on the slide here, you can see the schematic form of this expansion, focusing first on the case where all of the fields in the exchange are scalars, and where each family of poles is responsible for a family of non-analytic terms in the exchange momentum. So these non-analytic terms are what are the characteristic signal of a particle exchange. So these can't be emulated by a local quartic contact interaction. And in particular, the exponent of the exchange momentum is fixed by the boundary behaviors delta plus and delta minus of the exchange field. And the fact that you get contributions from both of these modes is a consequence of our choice of Bunch-Davis vacuum, where both of these modes reach the boundary at future infinity. On a practical level, this arises because in our expression for the exchange, the coefficients of these projectors, omega d and omega n, are non-zero. So if instead, for instance, only the coefficient of omega d is non-zero, then this second family of non-analytic terms is absent, because the poles that generate them have been cancelled by the zeros of this projector, omega d. So this scenario is perhaps more physically meaningful in anti-de Sitter space, where it corresponds to implementing the Dirichlet boundary condition. And a similar statement can be made about the Neumann boundary condition. So if only the coefficient of omega n is non-zero, then this family of non-analytic terms on the first line would be absent because their poles have been cancelled. And the nice thing about this general expression is that you can trace back the overall coefficients of each family of non-analytic terms to the sinusoidal interference factors coming from the constituent 3-point contact diagrams. So these products encode the interference between the different contributions at the level of the exchange. And this arises as a consequence of factorization, which we indeed use to fix our expression for the exchange. If instead the exchange particle has a positive integer spin, there's also an angular dependence, which in general boundary dimensions D is given by a Gegenbauer polynomial, where the degree of this polynomial encodes the spin information about the spin J of the exchange particle. So in our expression for the exchange, you can see that this angular dependence arises because the constituent 3-point contact diagrams now have a tensorial structure, which has been contracted together. So in the case where you have only external scalars, then these tensorial structures have been contracted together to form a scalar object. And this introduces this dependence on this angle theta here. If the external fields also have spin, there's of course also a tensorial structure. And from our expression, this tensorial structure can be worked out quite systematically because it's inherited from the tensorial structure of these constituent 3-point contact diagrams. So you can systematically work out what these are through their contraction. So far I focused on the on-shell exchange. So in the full exchange, another source of poles in U and U bar comes from this cosecant factor, which encodes the contact terms. And these are the red dots here. So because of this, the residues of these poles only ever contribute terms that are analytic in the exchange momentum. So in particular, the residue of the nth pole, which lies to the left of the integration contour, it generates a term that is proportional to the nth power of the exchange momentum squared. So where the coefficient of this term is given by the remaining Mellin integrals that are left over after you evaluate this residue. And what you can show is that this coefficient can be expanded in the inverse mass of the exchange particle. So these residues generate the effective field theory expansion of the exchange, where the non-perturbative corrections are generated by the non-analytic, are given by the non-analytic contributions which come from the on-shell exchange. So coming back to this full expression, let me emphasize that this is valid for a generic collection of internal and external particles. So throughout, I took these scalar dimensions and masses to be generic. But of course, in de Sitter, ultimately one is interested in unitary representations of the de Sitter isometry group. This expression is also valid for special representations like massless and partially massless fields, in the sense that in these cases, you have to plug in the corresponding gauge invariant 3-point functions into this expression for the exchange. And so gauge invariance actually manifests itself in quite an interesting way in this Mellin representation. And a simple toy example to consider is the cubic coupling of a massless spin J field to two scalars. So where gauge invariance requires that the lower helicity components in the corresponding 3-point correlator, gauge invariance requires that these lower helicity components don't contain bulk contact terms. So meaning that they're at most boundary terms. In particular, they don't have a singularity in this total energy variable, ET. So how does this requirement manifest itself in the Mellin representation? So we saw earlier that that contact diagrams contain, which is enforcing the constraint coming from these on the external Mellin variables. And when you make the helicity decomposition of your 3-point correlator, this Dirac delta function is present in each helicity component with an argument that is simply shifted by the number of longitudinal indices j minus m. So in order for your lower helicity components to be boundary terms, which we require to be consistent with gauge invariance, you need that each of these Dirac delta functions is accompanied by a factor that is equal to its argument. So this factor here is the same as the argument here in this Dirac delta function. And just like how boundary terms arise in momentum space, which I recall here, this precise combination, it represents a local boundary term in this Mellin bands representation, which arises from the integral over the bulk radial coordinate eta. So it's the integral over conformal time. So this factor multiplying the Dirac delta function cancels the bulk contact singularity that it encodes. So since 3-point correlation functions involving two scalars and a spinning operator are unique, In order for this structure to also be consistent with gauge invariance, these boundary terms have to emerge in the lower helicity components when you take the limit where the spin J field becomes massless. And if you do that, you find that this only happens if the scalars have the same mass. So this is consistent with what we already know about consistent cubic couplings of massless spinning fields to scalars. So this can only happen if the scalars have the same mass. And if you continue in this equal mass case, the corresponding boundary terms in the lower helicity components are finite and non-zero. So they give a corresponding non-trivial Ward-Takahashi identity. And this Ward identity is generated in this Mellin bands representation in quite a nice way. So it's generated by a finite number of poles which satisfy this constraint here. So essentially what happens is that this constraint sets to 0 the exponent of e to 0 in this boundary term. And so when you take the limit e to 0 goes to 0, you get a finite contribution. So in this way, for instance, for the helicity j minus 1 component, you obtain this Ward-Takahashi identity here. You can get similar expressions for the Ward identities for the lower helicity components, just more poles contribute, so they're a little bit more complicated. So now that you have your gauge invariant 3-point functions, which you know exist only if the scalars have the same mass, you can plug them into our expression for the 4-point exchange. And gauge invariance at quartic order, it famously constrains the cubic couplings G, which were completely left unscathed by the cubic analysis. And a simple example to consider is simply the exchange of a scalar generated by our cubic coupling with a single external massless spin J field. So to explore the constraints coming from gauge invariance, you take the full exchange amplitude, so the sum of the ST and U channels, and you contract it with the boundary momentum K1 associated to the external massless spin J. So you project onto longitudinal components. So what do you get? So first of all, you're happy because you get a term which gives you the right Ward-Takahashi identity. And this is inherited from the Ward identity that we saw on the previous slide.
Charlotte, 5 minutes. You have 5 minutes.
Yeah, I'm on time, don't worry. And you're happy because so you get the correct Ward-Takahashi identity. And this is inherited from the Ward identity at the 3-point level that we saw on the previous slide, because this is generated by the onshore part of the exchange, which factorizes into these constituent 3-point contact diagrams. And one of these is your gauge invariant 3-point function. But in addition to this, you get terms that violate gauge invariance. So these are in particular bulk contact terms, so they have a singularity in the total energy variable ET at quartic order. So to try to restore gauge invariance, what you can do is you can ask if there exists, if these offending terms can be cancelled by a local quartic contact interaction. By local, I mean with an interaction with a finite number of derivatives. And to proceed, you can classify the types of singularities in ET that can be generated by such a local quartic vertex. And what you find is that there are singularities in ET coming from the exchange which cannot be cancelled by such a local quartic vertex. So this is what gives you the constraint on the cubic couplings, because these offending terms then have to vanish by themselves. So this is somewhat parallel to Weinberg's analysis in flat space. So in particular, if you look at the helicity j minus 1 component, you get a constraint of this type here. So where the exponent of ET is some exponent that can't be generated by a local quartic vertex. And the factor that multiplies it is precisely the factor that comes out of Weinberg's analysis in flat space. So precisely the same hold in flat space, and also you can show in ADS as they do in flat space. So for instance, for spin 1 and spin 2, you get charge conservation and the equivalence principle, which was also obtained in a recent paper by Daniel Baumann and collaborators. And using our results, we could obtain the highest spin statement. And the precise statement is that if you allow if you restrict theories which have local quartic contact interactions, so with a finite number of derivatives, there's no consistent cubic coupling of a massless higher spin field to scalar matter, no matter what is the mass of these scalar fields. So to end with a few comments and some future directions, so let me emphasize that for fields of generic mass and spin, this Mellin bands representation captures the full analytic structure of these boundary correlators as a function of complex momenta. So in particular, what I mean is that for generic operators, it's well known that conformal correlation functions in momentum space are these like horrible generalized hypergeometric functions of multiple variables. this is some fact that you have to deal with if you want to study these objects at all. But what you can do is you can try to find useful ways to represent your generalized hypergeometric functions. And our perspective is simply that it's the Mellin representation that provides the analytic continuation of the hypergeometric series to the entire complex plane, which is cut along the positive real axis. And on the slide here, I just remind you of the Mellin representation of one of the simplest types of hypergeometric functions. And it's this representation which is responsible for establishing numerous properties of hypergeometric functions, such as transformation formula identities and asymptotic expansions, as well as the regularization of singularities. And you can use similar tools to study boundary correlators in this Mellin representation. And just like how you can obtain the hypergeometric series from the Mellin representation by applying the residue theorem, of course, you can obtain an expression for our exchange for any collection of particles as an infinite series expansion in multiple ratios of the momenta. But this would only be valid for a certain range of the momentum. So it's the Mellin representation that provides a more complete description. For special values of the parameters, of course, we know that hypergeometric functions reduce to simpler objects that don't require Mellin integrals to describe them completely. So you should think of this stupid identity here. Something of this type is happening. And this means that, so in these cases, so for the exchange, this happens for special representations like massless and partially massless fields, as well as conformally coupled scalars. So in these cases, you can completely lift the Mellin integrals. They're not needed at all. And in this way, we could get explicit expressions, for instance, for the exchange of a massless spin J field between conformally coupled and massless scalars, as well as the exchange in Yang-Mills and gravity. But
sorry, 1 minute.
Yeah, but despite these simplifications, we often found it more useful to work directly with this Mellin bands representation, for instance, like we did when studying these soft limits and also the Ward-Takahashi identities that we just saw. Looking to the future, there are plenty of diverse directions to explore, all as part of a program to systematically construct boundary correlators in this framework. And you would proceed in exactly the same way as I outlined in this talk. So you would focus on the on-shell piece, which you can construct by combining together these basic building blocks in a consistent fashion. Some obvious next steps would be higher points and loops to see what one could learn. And as you would expect, a nice parallel emerges with the Krukowski rules in flat space, as you can already see from writing down the expression for the Candy diagram in this form, as it immediately decomposes into the constituent tree level contact diagrams. And this is somewhat similar in spirit to existing generalized unitarity methods in ADS-CFT. And I believe David will be talking about these next. A little bit more speculatively, as one has to branch out, I would be curious to understand if any of these techniques would be useful in the context of flat holography, in particular to construct celestial amplitudes, where it sounds super naive at this point, but it would be tempting to say that the corresponding exchange on the celestial sphere takes a similar form, where of course you would have the appropriate boundary conditions and you would replace the 3-point contact diagrams with the 3-point amplitudes on the celestial sphere. The final point that I want to mention in some ways circles back to the first, and this is about the conformal bootstrap. So in recent years, we've seen that exchange Witten diagrams are useful objects to organize our 4-point correlation functions in the context of the so-called Polyakov-Mellin bootstrap. So I would just be curious to understand if any mileage could be gained, if at all, from using this Mellin bands representation in Wernson space, and if only to gain a foothold on the bootstrap of Euclidean CFTs dual to physics in de Sitter space. So yeah, I think I will stop here and thank you for your attention.
Yeah, thank you very much for a very nice talk. Let's see, I have a quick question. So you have these delta plus and delta minus, and they go complex, right, when the mass of the scalar, for example, exceeds the,
yes.
The horizon scale of the sitter.
Yeah, it's a principal series.
What happens to your results? Like you were writing formula where you could have either
limit. Sorry, I spoke of you, sorry.
So what happens to your results when delta plus and delta minus are complex conjugate? Is that still?
No, this is known, and actually it was known before our work. I think, I don't know the precise paper that identified it first, but definitely in this paper by Kahneman and Maldacena, they studied this scenario. So when the exchange particle becomes massive, So you see that these, so as you said, the scaling dimensions become complex. And this means that in these cases, instead of this kind of power law behavior in this soft limit, you get oscillations. So this is like the characteristic signal of these heavy particles that could be produced during the inflationary expansion. So you get an oscillatory signal, which is quite distinct. And yeah, there's also a phase that you might try to measure associated to these exchanges.
Okay.
That answer your question?
Yeah. I was just wondering if it modifies the allowed boundary conditions, because then there are two oscillating terms, right, from delta plus and delta minus.
No, I mean, so our boundary condition is essentially fixed by our choice of Bunch-Davies vacuum. So we're not fixing anything at the boundary at future infinity, because that would be in some ways acausal. So these representations are allowed regardless of this choice.
Okay, thank you. And I see a raised hand by Sandeep Trivedi. So Sandeep, you can ask the question. Sandeep?
Hi, can you hear me?
Yes.
Yes, I can.
Thanks, Igor. Thanks for a very nice talk, Charlotte. I've got two questions, if I can ask them, but let me start with the first, which is, I'm sorry, I'm a little rusty and I haven't kept up with your recent work, beautiful work. But just to ask you, as you know, in inflation, of course, there is a breaking of scale invariance because the inflaton evolves and rolls. But you can derive odd identities which include this breaking of scale invariance. Especially because the rolling is slow. So those can be written down, as you know, but now with all this nice progress in terms of Mellin amplitudes, does it help in solving those odd identities where you put in the breaking due to the slow roll? I was just curious.
You mean working under the lamppost of weakly breaking the conformal symmetries?
Yes, yes.
I mean, as you've seen, using conformal symmetry, we could get these within this Mellin formalism, we could get these very general expressions for any collection of particles using this Mellin technology. I mean, in this sense, solving the conformal word entity is quite simple in this framework, as I tried to outline. I'm not sure. I mean, the fact that these results were not obtained previously, restricting to usual techniques, I think it's quite useful in this sense. I'm not sure I fully understand the question.
No, the question was just that when you put in the breaking of scale invariance, because the dilaton is, because the inflaton is evolving and the Hubble constant is changing, etc. in inflation, you are not in exact de Sitter, and so the conformal symmetry is not exact, right? So the Watt identities in an inflationary background don't exactly preserve the conformal invariance, but they have corrections which are controllable because the breaking is small because of the slowly evolving dilaton. I'm sorry, inflaton. And I was wondering whether when you incorporate these corrections and use Mellin space techniques, you can now solve the corrected Watt identities also, or at least understand them more deeply than could be done previously. I was just curious, but
we haven't tried this. The only thing that we have tried was following an approach done by other people, especially this paper by Akanimed and Molasena, where you can obtain the leading corrections in the slow roll parameter by setting one of the legs to the background. So we're taking one of the legs to be approximately massless and obtaining the correction to the inflationary 3-point function. But no, we haven't tried to actually take the corrected conformal Watt density and solve using this Mellin formalism. Definitely there are advantages of using this Mellin formalism. You have a lot of analytic control and solving, not the corrected ones, but the normal conformal Watt densities, it amounts to just solving a polynomial equation in these Mellin variables. So it makes this procedure quite systematic. But I haven't tried to solve the corrected ones.
I think it might be fun to try and do, given all your nice work.
Yeah, this is true. Yeah, this is something. Yeah, thank you for the suggestion.
No, not at all. Yeah, if Igor will permit, I have one more question, but Igor, I can wait.
Yes, yes, please. Yeah, you can go
Okay.
ahead.
This is more vague, Charlotte, but I was wondering, of course, we don't have a string background of de Sitter or inflation, but to be just slightly ad hoc, let's suppose inflation occurred at the string scale, which it could, for all I know, because that could be lower compared to the Planck scale and consistent with the bounds on gravity waves not seen so far. So let's suppose that inflation occurred at the string scale. Then what you would have is an exchange, say if you look at your 4-point function, not of just one particle or a few particles, but let's say an entire Regge trajectory. And I was just wondering whether if you sum up such a trajectory or a set of contributions like that, is there a smoking gun in the inflationary correlators? Then say the three best would be the 3-point function for the scalar perturbations, but even let's take the 4-point graviton correlator, if that's a little easier to work with. Is there a smoking gun signal of a Regge trajectory?
And that's a beautiful question. This is something, that I've always wanted to, this is something that I would like to study in the future. I don't have an answer to your question because I haven't tried concretely. But of course, we know that in a perturbative framework, you have these bulk point singularities, this singularity in the total energy variable, ET. So I don't know if it would be a smoking gun, but definitely I would expect that this bulk point singularity would be vanishing. This would be some kind of signal of an entire tower of higher spins. I would try to guess, but any specific signal other than that, I don't know.
I vaguely remember there was some work a few months ago on related issues, basically studying spinning strings and de Sitter.
Who was it by?
A paper by Dieter Lust and collaborators, and
I see.
Yeah, putting some bounds on de Sitter from this Regge trajectory story.
I see.
There were a couple papers, but one was by Dieter Lust and collaborators.
I see. I see. Okay.
Sorry, I don't remember the details, but there was some of the words were the ones that you are asking.
Okay. All right. Thank you. Thank you, both of you.
Okay. So we have a question from Savan Harel. Savan, please go ahead.
Hello?
Yes. Yes.
Okay. Charlotte, thanks for a nice talk. I was curious about the flat space limits of these Mellin variables. So I think you briefly alluded to the norms of the momenta, like the singularity, that becomes transparent in the case of momentum space. Is it transparent in terms of these Mellin variables, and what are they in these Mellin variables, the flat space limit?
And the flat space limit, so in terms of a specific limit of these Mellin variables?
Yeah, if you can do flat space amplitude.
So analogous to the usual Mellin formalism in position space.
Right.
This we haven't tried. The only thing that we have looked at so far is this looking at the singularities in this total energy variable. So taking as you know, the residue of these poles gives the high energy limit of the flat amplitude. And in the Mellin formalism, you can translate these total energy poles into these kind of singularities in the sum of the external Mellin variables. So if you sit on this condition, then what you can we've only this recent, but if you sit on this condition, essentially what you get is the flat space amplitude essentially comes out when you isolate to this singularity here. So I don't know if this. I don't know if this is the analog of what is done in position space, but at least in this way you kind of extract the residue of this total energy variable, and then you get the high energy limit of the flat amplitude. But I don't think this is what you're looking for, right? You're looking for a precise analog of this nice limit in position space that depended on some people.
Yeah, it was also it's also good to know these are the analogs for the norms as well. So thank you.
Okay, are there any more questions or comments? Okay, if not, let's thank Charlotte again for a very nice talk.
Thank you for listening.
Now we will have about 7-minute break until the talk by David Meltzer. So thanks again.
Oxford.
Hi, David.
Right, sorry. I forgot to unmute myself. How are you?
Good, thanks. Do you wanna quickly check that everything's
Yeah, I'll check that.
the screen?
Let's see. Everything good? Can you see my cursor?
Yep. Mm-hmm.
Okay, perfect.
Great. Okay, so I think we've got about 5 minutes, right?
Yeah.
Yeah, we can start probably 11:59 my time. But
right.
Sorry, I'm looking at my watch, but.
Igor, perhaps I can make a quick announcement before you start.
Of course, of course.
Okay. This is for everyone who's listening. I'm going to start organizing the breakout rooms during David's talk. I'll still be paying attention to your talk, David, but in general, I'm going to start organizing the breakout rooms because it takes a little bit of a time to put people into the room. So I will put an announcement in the chat room as to what the rooms are. A reminder that we're going to have an additional room, which is the discussion, the panel discussion on inclusivity in string theory. That's hosted by Jen Het. And I will then prompt people to tell me which room they'd like to go into, and remind you that you can also move in between rooms. You just have to, again, let me know. And I will try and put you in the room that you'd like to go to. So that we keep things flowing. I'll try and have it set up before David's talk finishes, and then I'll start moving people in as soon as the talk is finished. Thank you.
Okay. Okay, thank you, Jeff. And it is a pleasure to have our next speaker, David Meltzer from Caltech, who will tell us about unitarity methods in ADS-CFT. And I will again give 5-minute and 1-minute warnings. Thank you.
Okay, thanks. So first, I want to thank the organizers for the invitation to talk and for organizing this very nice virtual strings conference during these very difficult times. So the work I'll be presenting will be about new developments in unitarity methods for ADS-CFT. And this will be based mostly on these two papers which came out last year, plus some work which should appear soon. So broadly speaking, the goal of this work is we'd like to use causality and unitarity to simplify perturbation theory in ADS. So in recent years, there's been a renewed study of holographic correlators. And by now we have a very good understanding of 4-point functions. And in particular, when you work to tree level in 1/n, and when the bulk theory is described by Einstein gravity plus matter. But I would say the general structure of correlators, when you look at higher points, higher loops, or finite alpha prime, are generally less understood. So we want to develop tools that can let us calculate some of the diagrams I've drawn here, at least in some limits. And the motivation for this work is we'd like to understand which CFTs have a local, weakly coupled gravity dual. And there's a famous conjecture that if you have a large N CFT with a very large gap in its higher spin single trace sector, then the bulk theory will be local and weakly coupled. So we're taking delta gap very large, so we're just decoupling all the bulk string A modes. And you can go further and you can show that if you impose causality in this large delta gap limit, you can show that the bulk theory is described by Einstein gravity, minimally coupled to matter at the level of the 3-point functions. So if I give you any 3-point function involved in a stress tensor and 2 single traces, the result is completely fixed up to 1 over delta gap corrections. And the answer you get matches the prediction from Einstein gravity in the bulk. So here these O's can also be the stress tensor. And this is a very nice result, and we like to understand how to push it further. So there's a natural set of questions to ask. So first you could ask about higher point functions. So for example, can we fix all the endpoint functions of the stress tensor in this large delta gap limit? In other words, can we fix all the graviton scattering amplitudes? There's another question about what role do loops play in constraining the space of theories? So we know loops are more sensitive to things like ADS-sized extra dimensions, but overall loop level consistency conditions have been less explored than the tree level counterparts. And finally, you can ask about relaxing this large delta gap condition. So can we start to understand the space of weakly coupled theories in ADS that also have higher spin particles. So one nice thing about working in ADS, when you're studying all these questions, is that we can rigorously constrain the space of theories using ideas from the bootstrap. But of course, the price we pay for this rigor is that doing computations in ADS is much more difficult than in flat space. So for example, I can give you this tree level exchange diagram, but we only know it in closed form when we have very special masses. And even then, the result has dilogarithms in position space. But by contrast, the corresponding flat space amplitude is very simple. It's just given by this rational function. So another motivation for this work is we like to try and understand ADS amplitudes at the same level as we understand the flat space S matrix in perturbation theory. This would help both in understanding which CFTs have a weakly coupled dual, and more generally understanding if there's any hidden structures or symmetries we're missing in a specific top-down model. So the first hint there should be more structure comes from the flat space limit. So I can take my 4 external operators and choose their wave packets so the bulk particles don't interact until they get to the center of ADS. So you can take a high energy limit that extracts the D+1 dimensional S matrix directly from the D-dimensional correlator. And then a question we like to understand is, do all the nice structures we know about in the flat space S matrix generalize to ADS, or do they only emerge when I take this limit? And in recent years, there have been similar questions asked in the study of de Sitter and inflationary correlators, particularly in the context of the cosmological bootstrap. So in this talk, I want to answer a very simple question and make a simple generalization. So I want to understand what are the ADS Kutkowski rules. And so what I'll present are 2 new bulk unitarity methods, which will simplify loop calculations in ADS. So these methods will match exactly with the previous boundary or bootstrap method, and they will also generalize the classic S matrix conditions to ADS. And for this part of the talk, for simplicity, I'll be restricting to scalar field theory in a rigid ADS background. And then as an application, I'll use unitarity to study the Regge limit in ADS CFT to all loop orders. And the main result here is that the correlator iconalizes at large with finite delta gap. And this is consistent with previous work on the study of bulk strings in ADS. So to get started, let me briefly review flat space unitarity. So we all know unitarity of the S matrix buys us a loop order. I pull off this matrix T, and then its imaginary piece is fixed in terms of lower loop data. And this becomes especially powerful if I have a dispersion relation. So I can write my amplitude M as a contour integral in the complex T plane. Then I deform my contour. I pick up the arcs at infinity and also these branch cuts on the real axis. So if I assume I can drop the arcs at infinity, what I find is that my amplitude is completely fixed in terms of its discontinuity, which is in turn fixed by lower loop data. So for the entirety of this talk, I'll assume I can drop any polynomial ambiguities, both in flat space and in ADS. But of course, it's an important problem in both contexts to keep track of them and make precise calculations. So with that being said, in practice, to compute this discontinuity, we of course use perturbation theory. We use the classic cutting rules. So what we do is we take a Feynman diagram, we cut it in 2. For each line we cut, we put a line on shell, and so this trivializes an integral. I can replace my propagator with some delta functions. So for example, this cut loop diagram just becomes a gluing of 2 on-shell tree graphs via a phase-space integral. And so this cut computes the discontinuity we're after. And we'd like to understand what's the analog of this dispersion formula and the cutting rules in more general spacetimes, particularly ADS? So the first part about the dispersion formula was answered by Caron Wout in 2017. So he showed that in CFTs, instead of studying the imaginary piece of the S matrix, what we should study is a double commutator. So I'll follow his notation and say we get this double commutator by taking a double discontinuity of our CFT 4-point function. And what he showed is that you can completely reconstruct your correlator once I know this double discontinuity. So this kernel K here is completely fixed by conformal symmetry. This is the analog of the flat space dispersion relation. And this formula is also very general, so it holds for all CFTs, including weakly coupled theories and a non-perturbative finite end theory. And it's proven very useful in the context of the bootstrap. But here we're specifically interested in holographic theories. And in that context, the cutting rules were previously unknown. So the goal of this work is to fill in that missing piece so we can have a bulk unitarity method. So I should say there's actually 3 different unitarity methods you can study in ADS CFT. So the first I'll call the boundary or bootstrap method. So here the idea is if I give you a double commutator, you can always insert a complete set of states and reduce it to an infinite sum over 3-point functions. And then you can try to fix those 3-point functions directly from the bootstrap equations. So this was the original method. It's been very well studied in the past few years to understand one-loop corrections, but I won't review that here. The second method I'll call the Euclidean bulk method. So this will be a bulk symmetry-based approach that allows us to compute the same 3-point functions. So here I do all my calculations in Euclidean ADS, and at the very end of my calculation, I Wick rotate the Lorentzian signature and study this double commutator. And then the final method will be the Lorentzian approach. So here we derive the Kutkowski rules directly in the Lorentzian ADS, and we use some more familiar ingredients, so things like ADS Whiteman functions and CFT momentum space. So the goal of this talk is I want to give just a brief overview of these 2 bulk methods and explain why they're useful in computing loops in ADS. So in the first part, I'll discuss this Euclidean method. And the Euclidean method works by directly factorizing your ADS diagram in terms of the physical exchange states. So in the language of the CFT, I need to introduce the block expansion. So all I do is I take my 4-point function, I insert a complete set of states, and then I sum up the contribution from a primary operator O and all its descendants. So these blocks G are completely fixed by conformal symmetry, and the lambdas are, of course, the OB coefficients. In a large N CFT, we also organize our operators in terms of single and multi-traces. Here, the important part is that these double traces will have the following form, and at infinite n, their dimensions just add. So a very simple block expansion to study will be when we take an S-channel tree-level exchange diagram and decompose it in the S-channel OPE. So this diagram has 2 kinds of cuts. There's the internal cut, dual to single trace exchange, and there's the external cut, dual to double trace exchange. And already from the block expansion, you can see how factorization will work. So the contribution of the single trace operator is completely fixed by the 1/n 3-point coupling, while the external cuts introduce some genuine 1/n squared data, things like corrections to the couplings and spectrum of my double trace operators. So in a holographic unitarity method, we want something that factorizes just projects onto this internal cut, which factorizes in terms of 3-point data. And we do this in practice by studying this double discontinuity. So what's nice about the d-disk is that when you act on a single block, all you get are some sine squared factors, and you see it has a zero, a double zero, at exactly the location of my double trace operators. So if I take the d-disk of my exchange diagram, I find this will project me onto the internal cut, which factorizes nicely. And the goal of the Euclidean method is to show how this generalizes to a more complicated loop diagram. So for example, we want to show the d-disk of the bubble projects onto the internal two-particle cut. More precisely, I'll make the following two claims. If I take the d-disk of the bubble and I study its block expansion, all I see are the double trace operators made from this internal cut. And the second claim is that this OP coefficient is completely fixed by the tree level contact subdiagram you find by cutting this bubble in two. And the main tool in this Euclidean method is the split representation for bulk propagators. So this is the same identity Charlotte used in her talk in a study of de Sitter correlators. So what I do is I write my bulk to bulk propagator as a product of two bulk to boundary propagators, where I integrate over their common boundary point x, and I have a spectral integral for the mass, this integration over nu. And the first important point is that these bulk to boundary propagators sit on the principal series. So they have dimension d/2 plus I nu. And since this doesn't correspond to the dimension of a physical local operator, also these new lines are off shell. But you can also see that this function p has poles exactly when d/2 plus I nu is equal to the physical dimension. So I'll call this the on-shell single trace pole. And then the way to think about this is that our integration over nu is analogous to the momentum integral in flat space, and our function p is analogous to the flat space propagator. So if you forgot about the d-disk and just use a split representation, you see that your diagram nicely factorizes. So I have two contact diagrams on the right, where these two operators have that off-shell dimension. And then roughly speaking, what the d-disk does is it puts these lines on shell. So I get a contact diagram squared, where the operators have their physical dimension. But this is just a cartoon. To make this picture more concrete, I need to introduce the conformal partial wave expansion. So what I'll do is I'll take each of these contact subdiagrams and I'll expand them in a complete basis of partial waves, where these also sit on the principal series. So instead of having a sum over all my local operators, I have a sum over spin, but I have a contour integral over dimension. And now all the physical data is encoded in the poles and residues of this function c. So what's nice about these partial waves is that they're an orthogonal single value basis in Euclidean signature. And they're also just a combination of two conformal blocks. So it's always straightforward to go from the partial wave expansion to the block expansion by closing my delta contour. More importantly for us is that they trivialize all the boundary integrals. So in a previous slide, I had a gluing of two contact diagrams. When I use this expansion, I get a gluing of two partial waves, but these satisfy this bubble identity where I'm left with a single partial wave and a delta function which removes one of my spectral integrals. So I won't go through the whole procedure, but the final result is that we find there's two sets of poles in our partial wave expansion. We have a set of poles for both the external and internal two particle cuts. But as I told you before, taking the d-disk projects out the phi-phi operators. So when I study this block expansion, all I see is this internal cut made from these two O operators. And more importantly, this OP coefficient here is completely fixed by the tree-level OPE function. So each of these came from a contact diagram, and I explicitly set new to its on-shell value. So this is the main result. The one-loop d-disk is completely fixed by on-shell tree-level data, which comes from performing an internal cut. And the reason this is simpler than trying to compute the full diagram is that I only had the on-shell poles and new contributing. If I tried to compute the external cuts or the full diagram, I would pick up an infinite number of poles in these individual OPE functions. So by taking the d-disk, I've traded a doubly infinite sum for a single term. So to recap this procedure, it's very simple. You take your loop diagram, you use the split representation to produce some lower loop off-shell bulk diagrams. You use some conformal technology, things like conformal integrals and the partial wave expansion, to perform all your boundary integrals. And here, by cutting a line, all I mean is I'm putting some spectral parameters on shell, and this is picking out some exchange states in the OPE. And what's useful about this method is that the output are some very well-studied CFD objects. So we get things like the 6J symbol for the conformal group, and also the conformal blocks. And the dispersion formula for these blocks and their sums are well known. So there's no obstruction here in going from the double discontinuity of a diagram to the full object, which isn't always the case when we study the flat space dispersion formula. And this method also generalizes to more complicated diagrams. So in our paper, we also studied this two-loop ladder. You can see that it naturally factorizes in terms of two tree-level 5-point functions. And our method carries over straightforwardly. We just introduce higher point partial waves and study their gluing properties. So all that being said, you may still have some questions about how to think about ADS unitarity. So here, we found factorization at the level of the exchange states. But if we have a local ADS dual, you may want a more refined notion. You may want to show correlators factorized directly in terms of the subcorrelators. You can also ask, how do we classify what the allowed cuts are? So in a previous slide, I drew some cuts, but I didn't tell you why some are allowed and some aren't. And finally, you can ask if there's a more general notion of cutting that relies less on choosing an OPE channel. So this is important if we want to define simultaneous cuts. So I'll try to answer these questions in the next section, which is about a Lorentzian method. So with this method, I'll give you a diagrammatic set of rules to compute the d-disk. And the two new ingredients is that I'll be working in the point gray patch drawn here, and I'll be using CFT momentum space. And the fundamental relation we need, I'll call the CFT optical theorem. And it says that the real part of a time-ordered correlator in momentum space is equal to a causal double commutator, where here A and R just stand for the advanced and retarded commutators. And it's important this identity doesn't hold for all momenta. So it only holds in the following kind of configuration. I take all momenta to be space-like, but K1 plus K2 is in the forward light cone, K3 plus K4 is in the backwards cone, but the other sums like K1 plus K3 or K1 plus K4 are space-like. So what I'm doing is I'm only putting K1 plus K2 on shell, and this is how I pick out this double commutator. And the reason this relation is nice is the left-hand side is a very natural generalization of the imaginary piece of the S matrix, but now for a full correlation function. In practice, this means we can compute the left-hand side diagrammatically. We just have to import Veltman's classic derivation of the flat space cutting rules to ADS. So what's nice about his derivation is it doesn't rely on the form of the flat space propagators. It just relies on some general identities among the Lorentzian two-point functions. So it's easy to import to ADS. Of course, it's the right-hand side, this causal double commutator, which actually appears in the inversion formula. So this is the object we're actually after. So usually we don't write this commutator with these causal restrictions, but in the space-time derivation of the inversion formula given in these two papers, you can note that there are causal restrictions imposed on how we integrate the double commutator. So with all that said, once I have this equality for my special set of kinematics, I can derive the cutting rules for the right-hand side. So to explain these rules, I need to introduce a little more notation. So here I'll be working in the Poincare patch, so I'll use the following metric. And later I'll be doing a Fourier transform in these x directions to go to momentum space. For my scalar field phi, I'll need to use two kinds of propagators. I'll have my usual Feynman propagator, which comes from the time-ordered two-point function in free field theory. And I'll need a positive energy propagator, which comes from this Whiteman two-point function in free field theory. Similarly, for the Boek-de boundary propagator, it also comes in two versions. I just take one point to the boundary. So now I can tell you what the cutting rules are for the real piece. So if I assume that my momenta runs from the left to the right, the rules are simple. For each line I cut, I replace my Feynman propagator by the positive energy propagator. For the left half of this diagram, I use the regular Feynman rules. For the right half, I use the complex conjugated rules. For each point to the right of my cut, I multiply by -1. And finally, I sum over all cuts, which are consistent with momentum conservation. So these should, of course, look familiar. The only difference with the flat space rules is really this third one, because in flat space, we amputate our diagrams, but we don't do that in ADS. So once I have this set of rules, I go to my special kinematics, and that gives me the cutting rules for the double commutator in the same configuration. And then if I want to go to more general momenta, what I use is that these causal restrictions in position space gives me analyticity in momentum space. So this is the usual statement about Laplace transforms and is how we prove that the Whiteman functions in position space are analytic. So the result is that once I know the double commutator in this configuration, I can analytically continue to general momenta to reconstruct the full object. So this is the main result. This gives us the cutting rules. And now I just want to make a few comments about these rules. The first is that the cuts we find with this method are exactly the same as the previous method. But now I can tell you why some cuts vanish and some don't. So what's important is that these Whiteman propagators only have support when the momentum is in a forward light cone. But here I've extracted this double commutator by working with space-like external momenta. So this means external lines cannot be put on shell. So this method explains why the following cuts of some loop diagrams don't correspond to any exchange states in the OPE. I need time-like momenta flowing through my cut, but each operator on the left has space-like momenta. So this is a somewhat surprising result. It tells us the double commutator has less cuts than the real piece of a time-ordered correlator and is, in a sense, the simpler object. This is also nice because we know from the dispersion formula, we can completely reconstruct the correlator once I know the double commutator. On a more practical level, you could ask, how do these cuts simplify the actual calculations? So in ADS, our propagators are, of course, more complicated. So in momentum space, it's expressed by this product of two Bessel J functions. The denominator takes the usual form, but I also have this integral over P. But just as in flat space, putting a line on shell removes the P integral, so I get just a product of two Bessel J functions with some restrictions on the momenta. And this representation is also nice because it tells us there's a split representation for these on-shell propagators. An on-shell bulk-to-bulk propagator is just the product of two on-shell bulk-to-boundary propagators divided by this power of k, which you can recognize as just dividing by a CFT two-point function. So this is similar to the split representation I gave before, but now I don't have any spectral integrals. The lines are directly on shell. So this tells us that cutting a diagram will factorize it in terms of some on-shell subdiagrams. And it also gives a very nice interpretation. It tells us how to think about a cut diagram as a sum over states. So now if I cut an exchange diagram, on the right-hand side, I get two 3-point Witten diagrams where these undotted lines are my usual propagators, and the dotted lines are the Whiteman propagators. In the bulk, these are the non-normalizable and normalizable solutions to the bulk equations of motion. And the difference between the two is one is a Bessel K function, and the other is a Bessel J function. So these objects have been studied before. A Witten diagram where I replace a bulk-to-boundary propagator with a normalizable mode are known as transition amplitudes, and they've been used in the study of ADS recursion relations. So then there's a natural interpretation. Our integral over the forward light cone is just our sum over states. And of course, the states of our ADS theory are just given by quantizing the normalizable modes. So one thing I want to emphasize is that to derive the cutting rules, we just use some diagrammatic identities, but we find that the final answer matches our physical expectations for what a cut should do. So to give a recap of this section, with this Lorentzian procedure, we use space-like momenta to relate the real part of a time-ordered correlator to a causal double commutator. We compute the cuts for the real piece using standard techniques, and then we analytically continue in the momenta to reconstruct the full double commutator. So this method tells us how to factorize diagrams directly in the bulk, and also gives a classification of bulk cuts and their relation to states. And this method also carries over to all higher point functions. So now we have a funny reversal. So in the past, we had a 4-point dispersion formula, but we are missing the cutting rules. Now we have all the cutting rules, but we don't have the higher point dispersion formula. States, and of course, the states of our ADS theory are just given by I think something normalizable modes. Someone has their mic on, I think. That to derive the cutting rules, we just use some diagrammatic identities, but we find that the final answer matches. Okay, sorry about that. There's a delay, I guess. Okay, so I think it's an open, interesting question to understand the higher point dispersion formulas and their connection to these Lorentzian rules. So in the remaining time, I want to discuss an application of these ideas to a physically interesting problem. So the study of the Ricci limit in ADS CFT. So in particular, I want to study high energy fixed impact parameter scattering in ADS. And in the CFT, this is described by conformal Ricci theory. And the nice thing about this limit is that it's very sensitive to the high spin spectrum. So things like gravitons and higher spin particles. And this is the limit people study to derive causality bounds. So if you recall that I'm denoting the bulk higher spin scale by delta gap, then the limit I study is when the bulk energy S and delta gap are both large. And I'll study this limit to all orders in 1 over n. So to give a picture for the Ricci limit, it just corresponds to taking 4 scalar operators and boosting them all to null infinity at the same rate. So in the bulk, I get this picture, and my particles are setting up the high energy scattering. More precisely, I'll work with these light cone coordinates and choose the following configuration. And then I take the limit where rho and 1 mass per bar go to infinity with the product held fixed. So the actual distance between my identical operators is kept fixed as I send them to null infinity. So if you study a single exchange diagram in this limit, we get the classic Regge growth. My correlator grows, and the growth is set by the spin of the exchange particle. There's a similar growth seen for the anomalous dimensions for the phi psi operators. Here I'm taking n and L large with the ratio held fixed. Then, of course, if I have a theory with an unbounded number of higher spin particles, I should take the sum first before I take the Regge limit. So if I sum over the leading trajectory, what I find is I can replace this sum by the exchange of a funny non-local object called the Pomeron. So this has spin slightly below 2. And so my correlator and anomalous dimensions still grow in the Regge limit, but now with this effective spin J star. I'll need to make some technical assumptions, which you can ignore this, but I'll assume that the spin of my trajectory is polynomial in the dimension. And I'll assume that when I take delta to be avoided delta gap, the spin grows quadratically. This, the last one is proven in flat space. So with all that said, I can now take my two Pomeron exchange diagrams and use this unitarity method to glue them together. And then I take this S-channel cut. So in the CFT, I'm just summing over my double trace operators where I square their tree level anomalous dimensions. And if you plug this into a dispersion formula, you find your one loop correlator grows twice as fast as the tree level result. So this growth may appear problematic at first because we know there's a bound on the Regge limit for a non-perturbative finite end theory. And it says that J star is less than 1. And the resolution to this problem is familiar from flat space. So what should happen is that when I sum over all loops, here it will be a sum over all the Pomeron ladders, the correlator should iconolize.
Sorry, five minutes.
Okay, thank you. So this will be clearest when we work in impact parameter space. So I'll introduce two new variables, S and L. S is the energy squared, and L is the impact parameter on this blue line, which is hyperbolic space. And I'll denote my correlator by this curly B. And what the iconal ensemble says is that when I sum over all loops, my correlator should exponentiate in impact parameter space. So if delta is a tree level phase shift, then I just get e to the I delta. And now we can compare this ensemble with the prediction we get from unitarity. And what we find at one loop is the deviation between the two is suppressed by 1 over delta gap to the 4th for both the real and imaginary piece. And this pattern continues to hold to all loops. So we see the iconal ensemble is working in this large delta gap limit. And this matches previous work on the bulk Pomeron. In these two papers, where they also found exponentiation at strong coupling. So then the natural question is, what happens at higher orders in 1 over delta gap? So if we impose that our correlator iconalizes, this tells us that this will impose some constraints on our theory. So it's not automatic from the CFT perspective. If I give you some leading trajectory, that if I keep using this unitarity method, that I'll get e to the I delta in impact parameter space. So this is an example where by studying loops and imposing some physical consistency conditions, we can derive constraints on the CFT spectrum. Specifically, we have to fine-tune our contributions to this double discontinuity. So I should say the full constraints of iconalization haven't been worked out. There's interesting new effects like tidal excitations, which still need to be studied. But I think it's an interesting open problem to understand if iconalization can be proven from the CFT perspective, or alternatively from a more bulk perspective. So that's all I want to say about the Regge limit. Let me wrap up. So the summary is that we have two new bulk methods. The first uses harmonic analysis to factorize ADS diagrams, and the second directly generalizes the classic cutting rules to ADS. And these give a new window into our understanding of ADS high-energy scattering. There's many other applications, which I don't have time to discuss. You can use these methods to give a precise map between the previous boundary method and the bulk loop expansion. The Lorentzian method generalizes to weakly coupled CFTs. And there's interesting physics when you study the bootstrap and the Regge limit. And you can find a map between the bulk phase shift at large with finite delta gap and the double trace OPE data. And I think there's a lot of interesting questions to consider. And I think the main takeaway is that ADS CFT correlators really aren't that different from their flat space counterparts. So I think we're just at the beginning of understanding loop correlators in ADS. And it'd be very nice if we could import other techniques like generalized unitarity, the double copy relations, or the picture of polytopes to ADS. It would also be interesting to understand applications to other spacetimes like de Sitter or inflationary spaces, as we heard in Charlotte's talk. ADS technology can be very useful in other spacetimes. It would also be nice to make a connection to correlators in Mellin space. So holographic correlators in Mellin space have a very simple form, and their structure is analogous to that of scattering amplitudes. But if we want to understand how far this analogy goes and how much of the loop structures carry over, I think understanding these cutting rules in Mellin space is an important first step. And finally, there's other high-energy limits to study, like high-energy fixed angle scattering. And it would be interesting to understand what conditions we have to impose on the CFT for the emergence of gross Mendel behavior. So that's all I have to say. Thank you for your attention.
Thank you very much, David.
Yeah.
Okay, so questions? Are there any questions from the audience? Yeah, Steve Giddings, please.
Thanks. When you think about high energy fixed impact parameter and are discussing iconalization, in flat space, if you go to high enough energy, that ultimately breaks down because you have other higher loop graviton diagrams that contribute. So I guess you're just not considering them at this point, or how are you handling, or what is the story with that in this context?
Yeah, so at this point, we're not considering them. There's the two effects that are more important at this level are trying to understand the tidal excitations. So yeah, I'm working at large, the finite delta gap. So there's the other effects like tidal excitations or long string creation. Even those aren't that well understood beyond tree level and 1 over n. If I work at finite delta gap. So here I'm taking large delta gap, and that's simplified things. Yeah, I don't have anything to say. There's other effects like, yeah, there's other loop effects involving gravitons, but I don't have anything to say about that.
Yeah, specifically in the flat space context, if you think about it, you go fixed impact parameter higher and higher energies. Ultimately, you have diagrams that correspond to inserting tree level graviton diagrams in between, and then you can build up effectively black hole formation in that context. But that's probably a lot harder to treat at present, I imagine.
Yeah, here it's a simpler problem. We're just trying to understand really the analogy of even understanding just string scattering at tree level is difficult. and trying to keep track of all those stringy effects. So like in the original work by like Amati, Ciafaloni, and Veneziano, they had this beautiful picture where things were iconizing an impact parameter space. And that was understood. And then that's like the first order problem. Even that isn't understood in ADS. So yeah, there's simpler problems which are, still need to be solved.
Okay, thank you.
Okay, any more questions?
I have a question, if I may.
Yeah, please go ahead.
So in QCD, so at weak coupling, people have studied a lot this physics of the Pomeron, and well, for them it's also a problem because even at weak coupling, the Pomeron has an intercept bigger than 1, so it will violate unitarity. So this is a big topic in QCD of resumming and unitarizing the Pomeron, and there's this saturation phenomena. So did you try to compare your predictions from unitarity methods in ADS with the predictions from this QCD approach, from this field theory approach?
I haven't, but that it would be an interesting problem. I don't know that working in ADS would help in comparison to flat space. I mean, what we're doing in ADS is, I feel like it's always like a few steps behind flat space, and so this is just repeatedly using a dispersion formula and the Freisach-Gribov formula. So probably if it works in ADS, maybe it would be interesting to study iconization with those methods in flat space first, like understanding the classic S matrix constraints.
Sorry,
I guess. Sorry, what are you saying?
Maybe I was not clear. Let's be concrete. So suppose you take n equals 4 superring mills at weak coupling. So we do this Pomeron, and we have this. This bubble. We know how the Pomeron at leading order in 1/n contributes, right, from conformal Regge theory. Now I think your mechanism explains how to go to order 1/n to the 4th, I guess, right? The next order, the first loop of the Pomeron, where I exchange 2 Pomerons.
Yeah.
So I think from your methods in practice, you really have a prediction for what the next order, like 2 Pomeron exchange is, and that could be compared with what a pure field theory method from, say, applied to n equals 4 superring mills would give. So it would be a very concrete comparison.
Okay, so yeah, you want to compare the bulk unitarity method for the very stringy Pomeron with the prediction from the boundary n equals 4. I mean, I think it could work. I think it will work, but I think I think it would be simpler to study just if you're doing sorry. Yeah, I would think it'd be simpler just to work in flat space, though. I mean, and I mean, this unitarity method is the same as the old flat space unitarity, so I would think it would be simpler there. Although we definitely could make a comparison with this Regge theory and unitarity method. And yeah, it would be interesting to. Sorry, I thought you meant originally. I thought you were talking about QCD in the bulk, which is a different problem. Okay.
Yeah, I think there was some work on Pomeron and n equals 4 superring mills and extrapolation between weak and strong coupling. I've seen many papers of this sort.
Yeah, it does a lot of beautiful integrability work. Yeah, I guess, okay, I haven't really, I'm not sure if you're studying weakly coupled with n equals 4 and you're using these unitarity methods, I think it would be equivalent to just using the unitarity methods in flat space. And I think it'd be simpler to think in terms of flat space diagrams, but it would also be interesting to extract some ADS physics or understand if the ADS perspective helps. Yeah.
Okay. Thank you. Any more? Oh, there is Gabriele Veneziano.
An important issue concerning how you unitarize a supercritical Pomeron is whether the three Pomeron coupling, at tree level, at the lowest level, is zero or non-zero at zero momentum transfer. This is what distinguishes two kinds of region field theory in the old days. So I wonder whether your method would be able, from the ADS CFT point of view, to understand whether the three Pomeron coupling is zero or non-zero. Do you know that?
I don't, but it's an interesting problem to understand treating the Pomeron more as an external operator. So I'm going to say, make a brief connection. It won't really answer your question, but I'll just say that with this unitarity method, when we cut this diagram this way and we feed it into the dispersion formula, it tells us now about this horizontal cut, which is the coupling of two Pomerons to two local operators.
That's right.
So this is, I think this is a simpler problem, but it's generally less understood how to treat the Pomeron as an external operator. So there is a definition of the Pomeron in terms of a light ray operator, where you analytically continue the graviton radial trajectory, and the Pomeron sits at a certain point. So this is just to say that holographic calculations for the bulk Pomeron are, I think,
I didn't mean to
less
take
understood
the
as far as
Pomeron
I
as
understand.
external. Yeah, I didn't mean to take
as
an external state, but just to construct a more complicated loop diagram. Not loop diagram in which three Pomerons come together.
Oh, I see.
In the bulk.
Yeah. Okay. I haven't thought of. I haven't.
Start with a 6-point function and then have,
Yeah.
each pair of them coupled to a Pomeron, which then couples to itself.
Oh, okay. Yeah. So
linear coupling. Yeah.
Yeah. So you want to take a 6-point function and take the Regge limit for like
function. Take the what used to be called the triple Regge limit or something like this.
Yeah.
You have two Pomerons. Because that is an important quantity for the Regge-Gribov calculus. In the old days, this is how people were discussing how you unitarize a theory in which the bare Pomeron is above 1.
Okay, yeah. So I don't think I've anything. I think this method. I think there is a way of extracting it from CFD data or from more bootstrap ideas. If you study a 6-point function of local operators and take the Regge limit in pairs, there may be a way of there should be a way of constructing.
Then you have to take a special
coupling.
kinematic limit. Yeah.
Yeah, but it would be interesting, but I haven't looked at that.
Thank you. It's just a remark.
Thank you.
All right. Well, that was a good discussion. Are there any more questions? Or there were some comments on the chat, so I guess all of this can continue in the breakout rooms. So I'd like to, if there are no more comments, let's thank David again. And I'd like, since this is the last talk of today, I'd like to thank all the speakers. And now we can go to breakout rooms as Jeff informed us.
Thanks, Igor. Just want to update everybody. So I'm busy setting up the breakout rooms. I've posted in the chat room what the breakout rooms are. Today we're gonna have the breakout rooms running for about 2 hours because a lot of people want to participate in different sessions, and I think we'd like to allow people to do that. I'd like to also remind participants that you can participate in the Slack channel discussions as well. These have been running pretty much the whole time, and they will be, they don't get closed. They'll be running throughout the conference, and I don't see any reason to close them, so we'll keep them open in perpetuity. So please do continue your discussions there. So the way the breakout rooms work is I assign everybody to the breakout rooms. And then if you would like to change breakout rooms, you can leave the room and then ask me again to put you somewhere else, and I'll do that as soon as I can. And then after the 2 hours, the rooms will shut and everybody will come back into the main room, and we'll close the session for the day. But depending on how the discussions are going, if we need more time, then we can assign more time to the rooms. So I've posted in the chat the rooms. They are essentially labeled by the speakers. So the first room is Shiraz Minwala's. The second room, we've grouped João Penedones, Andrea Pum, and Charlotte Slight's talks into one room. Room number 3 is David Meltzer's talk from just now. Room number 4 is the inclusivity in string theory. And room number 5 is a social room where people can just chat if they so choose. So again, just send me a private message in the chat room, and I'll assign rooms. It'll take me, there are about 180 participants to be assigned. It'll take me possibly about 15 minutes or 20 minutes. So I will open up the rooms at about 1/4 the hour. It's now 5:02. I will open the rooms at 1/4 the hour.
Jeff, how do you go into the rooms? What do you actually have to do?
I will teleport you there. You don't have to do anything. You'll get an invitation that says join this room. You click on the invitation and it'll just send you into a breakout room. And then once the room closes, yeah, it'll appear on your screen. And I've pre-assigned the speakers to their own rooms just to start the discussions.
some